Okay, let's unpack this. Imagine trying to draw a line in the sand, but with a truly complex mathematical function. What if that line wasn't just a simple boundary, but something as intricate as the edges of a cube? And what if a special kind of mathematical function, a harmonic one, could actually vanish or become precisely zero exactly on those edges without being zero everywhere else? This seems counterintuitive, doesn't it? Today we're diving deep into the fascinating world of harmonic functions and their zero sets, the specific places where they hit zero. Our mission is to navigate the groundbreaking insights from Ioann Vasilyev's paper, aptly titled On the Zero Sets of Harmonic Polynomials. We're going to dissect its core arguments, understand the elegance behind its mathematical proofs, and, well, uncover its surprising answers to questions that have puzzled mathematicians for decades.
Right. And this paper offers a rigorous and really captivating exploration. It delves into fundamental definitions with precision, unpacks intricate derivations step by step, and honestly, it opens up entirely new avenues in the ongoing study of harmonic functions. Crucially, it directly addresses a problem from the famous Scottish book from 1936, a legendary collection of challenging mathematical puzzles. It also significantly extends recent results in the field. We'll be going through this source with meticulous care, breaking down every significant detail, from the exact notation used to the underlying mathematical reasoning. The goal is to give you a truly granular and hopefully satisfying understanding.
Yeah, whether you're refreshing your knowledge for maybe a high-level meeting, or you just have an insatiable curiosity about how complex ideas are built, or maybe you're simply on the hunt for those aha moments that unlock seemingly impenetrable concepts. This deep dive will equip you with a foundational understanding of a topic right at the intersection of classical analysis and modern mathematics. You'll witness firsthand how mathematicians tackle seemingly impossible questions and, step by step, construct entirely new knowledge.
Okay, so let's begin our journey at the very foundation of this paper, starting with section 1, the introduction. On what would be the first page of the paper, the author immediately introduces us to the rigorous definition of harmonic functions. We use the notation H, that denotes the space, or you could say the collection, of all harmonic functions defined within a specific region or domain. This domain, A, it's itself a subset of ARD.
And ARD, for listeners who might not be familiar with that notation, what does the D signify there?
Excellent question. Yeah, the D in RD is a natural number, like 1, 2, 3, and so on. It signifies the dimension of our Euclidean space. So R is just a line, R has a plane, R is the three-dimensional space we live in, and ARD is just a generalization to any number of dimensions D. The definition then states that a function f is considered harmonic in this domain if its Laplacian, denoted by the triangle symbol, is equal to 0 everywhere within that domain. Formally, this is written as if is 0.
Okay, if is.
Let's meticulously break down that Laplacian notation and what if is code truly means, because it's absolutely central to our discussion. The Laplacian operator is if. It's essentially a compact way to write the sum of all its second partial derivatives. When we say if it's ifis, it means that if you take the second partial derivative of if with respect to its first coordinate variable x here, and the second coordinate variable x, and so on all the way up to x, and then you sum all those derivatives, the result must be 0. In maybe plainer terms, it's s is fos plus f plus if plus if.
That's quite a mouthful of derivatives. What does AVA equals 0 mean conceptually, or even physically? Is there an intuitive way to grasp this idea of a function being harmonic?
Absolutely. There's some beautiful physical interpretations. The most common and, I think, intuitive one is thinking about steady-state heat distribution. Imagine you have a metal plate, right? And you've heated certain edges and maybe cooled others. After a while, the temperature across the plate will stabilize and won't change over time. It reaches equilibrium. At that point of equilibrium, if AV represents the temperature at any given point, its Laplacian alpha will be 0. It means there are no net sources or sinks of heat within the region, and the heat flow is perfectly balanced. It's smooth.
Ah, smooth balance. I like that.
And this concept of equilibrium or balance, it actually extends beyond heat. In potential theory, it describes the gravitational or electrostatic potential in a region free of mass or charge. In fluid dynamics, it can describe the velocity potential of an incompressible irrotational fluid flow.
Yeah.
So when a function is harmonic, it's describing a state of perfect balance, smoothness, and crucially, absence of internal sources or sinks.
That's a fantastic way to put it, a state of smooth balance.
Yeah.
Building on that, the paper then introduces something called a uniqueness set, denoted S, which is a subset of our domain A. This sounds like a powerful concept where vanishing on just a small part of the domain can force the function to be 0 everywhere. Is that right?
Precisely. The formal definition states that S is a uniqueness set for the space, HA, if for any function f that is harmonic in A, so f h array, the condition that f vanishes on S, written as fs equals 0, implies that fx equals 0 for all x in the entire domain. In simpler terms, yeah, if a harmonic function is 0 on this specific set S, it has no choice but to be 0 everywhere else in its domain. It's like a mathematical domino effect. The paper makes a crucial clarification right away. Its focus is exclusively on uniqueness sets for HRD, meaning harmonic functions defined over the entire Euclidean space, RRD. Unless explicitly stated otherwise, all harmonic functions discussed are assumed to be defined and harmonic across the whole space.
Yeah.
This simplifies the discussion by removing complexities related to specific boundaries or finite domains, allowing us to focus on the inherent properties of the functions themselves.
Right. So if our harmonic function just vanishes on any set, does that automatically force it to be 0 everywhere? I imagine there are some obvious cases, as the paper puts it, where this is true, like if it vanishes on a really big or connected set, something like that.
That's an insightful question. And yes, there are indeed obvious or trivial cases, as the paper terms them, where vanishing on a certain set does immediately imply the function is 0 everywhere. The paper highlights two such scenarios. If a harmonic function vanishes on an open set, or if it vanishes on a closed rectifiable curve, it must be identically 0. The core reason for this lies in a fundamental and extremely powerful property of harmonic functions known as the maximum principle.
The maximum principle. Okay, that sounds important.
Oh, it's absolutely critical to understanding why some 0 sets are trivial and others are, well, profound. The maximum principle for harmonic functions essentially states that a non-constant harmonic function cannot achieve its maximum or minimum value in the interior of its domain. Instead, these extreme values must occur on the boundary of the domain, always on the edge, so to speak. Now consider a harmonic function f that vanishes on an open set. An open set is a region where, for every point within it, you can draw a tiny little circle or sphere around that point, and the entire circle or sphere is still completely contained within the set, like the inside of a circle, but not including the circle itself. If our harmonic function f is 0 across this entire open set, and if we were to assume f is non-zero somewhere else, then within that open set, f would be constantly 0. This means it achieves both its maximum 0 and its minimum 0 values in the interior of that open set. But the maximum principle strictly forbids this for any non-constant harmonic function. Therefore, the only way for a harmonic function to be 0 on an open set without violating the maximum principle is if it is constant and equal to 0 everywhere across its entire domain. It's forced.
Ah, so being 0 inside forces it to be 0 everywhere because it can't peak or dip inside.
Exactly. And the same powerful logic applies to a closed rectifiable curve. While a curve isn't an open set, the maximum principle, along with related theorems like the uniqueness principle for harmonic functions, extends to show that if a harmonic function is 0 on such a boundary, for instance, the boundary of a square or a circle, it essentially forces the function to be 0 throughout the interior region enclosed by that curve. And if the function is defined as harmonic in the whole space, then by extension it must be 0 everywhere. So these are the trivial cases because fundamental properties of harmonic functions immediately lead to the conclusion of the function being identically 0. The challenge arises when the 0 set is more sparse or, geometrically complex.
I understand. So if it's so easy in those cases, where does the deep dive truly come in? Where's the actual intellectual challenge in this problem?
Well, the profound challenge stems from the sheer difficulty of giving a general description of what constitutes a uniqueness set for HRD. The paper explicitly states that such a general description appears out of reach, even when we restrict our consideration to sets that are finite unions of affine subspaces.
Affine subspaces, like lines and planes, but maybe not through the origin.
Exactly. Generalizations of familiar geometric concepts like lines, planes, and hyperplanes, flat subsets of R that don't necessarily have to pass through the origin. The paper cites compelling examples from previous research, specifically mentioning reference 14, of non-analytic curves that can be non-trivial uniqueness sets. This highlights just how intricate and, frankly, counterintuitive these sets can be. The trivial cases we just discussed, like vanishing on an open set, are simple because the function's behavior is highly constrained. But for more complex, discrete, or geometrically irregular sets, pinpointing the implications for the function's global behavior becomes extraordinarily difficult. That's the real puzzle.
Okay, so D dimensions is tough. What about the plane when D2? Is that case any easier to answer?
Interestingly, yes, the 2D case, the plane, is significantly more approachable and has a much simpler answer. The paper illuminates this by cleverly leveraging the properties of complex polynomials. In the plane, we can conveniently think of points as complex numbers, z and c. If we have a finite collection of distinct points, let's call this set E equals for j from 1 to n, where each pj is a specific complex number. We can construct a polynomial PE, defined as the product of zpj for j ranging from 1 to n. So pz is just zp.
Right, a standard polynomial with roots at the points p.
Exactly. And this polynomial PEZ possesses some absolutely crucial mathematical properties. It is holomorphic, which is a very strong property in complex analysis. It essentially means it's complex differentiable everywhere in its domain. This PE is, in general, non-zero, but critically it vanishes only at the specific points contained in the set E. Now, here's the elegant connection to harmonic functions. A fundamental result in complex analysis states that the real part and the imaginary part of any holomorphic function are, themselves, harmonic functions. So if PEZ is holomorphic, then its real part, denoted PE, that's the notation for the real part, is guaranteed to be a harmonic function. And since PE is zero exactly at the points in E, its real part EV will also vanish at those same points. So this EPE becomes our desired harmonic function that is zero only on the finite set E and non-zero elsewhere. This simple, elegant construction beautifully illustrates why the 2D case is far more manageable and provides a stark contrast to higher dimensions.
That's a really clever trick using complex numbers, and it sets the stage perfectly for a truly historical problem that this paper directly addresses, doesn't it? The famous problem 151 from the Scottish book. I've heard snippets about the Scottish book and Roland Wive's 1936 problem, and wasn't there a fondue prize involved?
Indeed, the Scottish book is more than just a notebook. It's a legendary piece of mathematical history. It was a notebook kept at the Scottish Cafe in Lwów, Poland, which is now Lviv, Ukraine, a vibrant intellectual hub where some of the most brilliant Polish mathematicians of the 20th century, giants like Stefan Banach and Stanisław Ulam, would gather between the 1930s and 1940s. They would spontaneously pose challenging mathematical problems to each other, often offering incredibly creative or humorous prizes for their solutions. For problem 151, yes, a fondue in Geneva was famously offered as the prize. It's a wonderful testament to the collaborative and playfully competitive spirit of that era.
A fondue prize. Love it. So what was the problem exactly?
Roland Wive, a Swiss mathematician, posed problem 151 on November 6, 1936. The problem statement is quite specific and, well, deceptively simple. Does there exist a harmonic function defined in a region which contains a cube in its interior, which vanishes on all the edges of the cube? One does not consider f equals 0. The crucial nuance here, which cannot be overstated, is that final clause. One does not consider f equals 0. If a function identically equal to 0 were allowed as a solution, the problem would be trivial, because the 0 function is obviously harmonic and vanishes everywhere, including on the edges of any cube. The true intellectual challenge, the heart of our deep dive, is to find a non-zero harmonic function that achieves this. This is where intuition often fails, and where the paper makes its profound contribution.
And the paper actually provides a positive solution. It explicitly constructs such a function, which is incredibly exciting.
That's absolutely correct. Theorem 1, presented on what would be page 2 of the paper, delivers the explicit and powerful answer. It formally states, for any natural number D3, there exists a non-zero harmonic function on the whole space R, which vanishes on the D2 skeleton of the unit cube QD. Let's take a moment to meticulously break down this statement, as it's packed with precise mathematical terminology. First, QD denotes the unit cube. This is defined as 12, 12. That just means its sides extend from magnitude 12 to 12 along each of the d-coordinate axes. Standard unit cube.
Okay, unit cube, but D2 skeleton. What's that?
Right. What exactly does the D2 skeleton mean in this context? The paper formally defines SKED as the k-skeleton of the unit cube. This is the union of k-dimensional faces of the unit cube. That is to say, the set of all points that belong to the boundary of the cube and have at least d-coordinates equal either to 12 or to 12. So for a D2 skeleton, we set k equal to DDO. This means the number of coordinates that are fixed at 12 must be at least D2, which simplifies to at least 2 coordinates.
At least 2 coordinates are plus or minus a half. So if D is 3, meaning a standard 3D cube, the D2 skeleton would be the 3, 2, 1 skeleton, the one-dimensional faces, which are the edges. That's a perfect match for the Scottish book problem.
Exactly. For a 3D cube, the one skeleton is indeed its edges. So Theorem 1 directly provides a positive answer to the Scottish book problem for D3, and then generalizes it elegantly to all higher dimensions where D3, 3. It asserts that for these dimensions, you can find a specific non-zero harmonic function that vanishes precisely on these edges, or the D2 skeleton, without being zero everywhere else.
That's a pretty profound result, overturning the initial intuition that might suggest it would have to be 0 everywhere. But the remark right after Theorem 1 says it's false for D2. Why is D2 an exception? Does it go back to the power of the maximum principle you explained earlier?
You're absolutely spot on. The remark explicitly confirms that Theorem 1 is indeed false for D2, and it's simply by the maximum principle for harmonic functions. Let's connect the dots here. In 2 dimensions, the D2 skeleton would be the 0 skeleton. This corresponds to the vertices of the unit square, the corners. If a harmonic function vanished only on the 4 vertices of a square, it would not necessarily be identically 0. The construction using complex polynomials we discussed earlier shows this. However, if the problem asked for vanishing on the edges of the square, which would be the 1 skeleton in 2D, that would effectively mean it vanishes on a closed rectifiable curve, the entire boundary of the square. As we meticulously discussed earlier, if a harmonic function vanishes on a closed rectifiable curve, the maximum principle dictates that it must be identically 0 inside the region bounded by that curve, and by extension, if it's harmonic in the whole space, then everywhere. So for D2, the edges, the 1 skeleton, would form a trivial uniqueness set. The problem becomes truly interesting and non-trivial, precisely for D2-3, because the D2 skeleton in these higher dimensions doesn't enclose a full D-dimensional volume in a way that trivializes the problem by the maximum principle. It leaves gaps, so to speak.
Got it. The geometry in higher dimensions is different enough.
Exactly. The paper then broadens the perspective slightly, touching upon nodal sets, which is simply the mathematical term for the sets where a function is 0. It highlights that the structure of these nodal sets of harmonic functions is not just an active area of research today, but also a topic with deep historical roots. It points to James Clerk Maxwell's seminal work from the 19th century, connecting it to the still-open Maxwell conjecture, which concerns the number of critical points of harmonic functions. This beautifully contextualizes the problem we're discussing within a rich tapestry of centuries-old mathematical inquiry. It also cites several recent influential papers. The references 16, 17, 12, 11, 7, 6 are mentioned to underscore that this isn't an obscure, fully solved corner of mathematics, but rather a vibrant, evolving field with ongoing, significant advancements.
So after all that build-up and historical context, how does Vasilyev actually construct this mysterious, non-trivial function? The paper provides a specific and rather elegant formula for f dx.
This is truly where the mathematical elegance of the solution shines through. The paper provides the explicit formula for the function f dx sd by 1xd, not 1a. Let's meticulously break down this notation to ensure absolute clarity. The large symbol, that's a product symbol, similar to how juice denotes a sum. The subscript 1aj specifies the indices for this product. It means we are multiplying terms for all unique pairs of I and j such that I is strictly less than j, and both I and j range from 1 to d. So, for example, if d3, the indices would be 1a2, 1a3, and 213.
Right, all the pairs where the first index is smaller than the second.
Precisely. The full product for D3 would then be x zeros.
So it's x smaller than x, and finally x ordos. Got it. And the paper even includes a figure 1 illustrating the nodal set of F3. I'm picturing these specific red lines precisely outlining the edges of the unit cubes in 3D.
Indeed. Figure 1 provides a powerful visual confirmation that for F3, its nodal set, the collection of points where the function is 0, consists precisely of the lines that correspond to the edges of the unit cube. It's a direct, intuitive visualization of the solution to the Scottish book problem. The paper also makes a very important remark. This f dx function strongly resembles van der Maan polynomials. While f dx uses squared terms, x on CLI, a classical van der Maan polynomial typically has the form or, ij. The striking resemblance is not coincidental. It's actually a critical clue and the cornerstone for the proof of its harmonicity.
Interesting. So it's related to something known.
Very much so. And the paper further emphasizes that f dx is not the only function that satisfies Theorem 1. It offers an alternative function, gx, defined as gx apio1 ASO11. This function also works as a non-zero harmonic function vanishing on the D2 skeleton. Furthermore, it introduces eights, xex, xe1, x1, 3. This a-stake is particularly interesting because it's a Laplace eigenfunction, meaning that applying the Laplacian operator to 8x simply returns hx, multiplied by d, i.e. ax equals dhx.
So the Laplacian just scales it.
Exactly. These remarks are significant. They highlight that the solution to the Scottish book problem isn't unique, and more broadly, they open up deeper questions about classifying all such functions, which is a much more complex and active area of research.
Okay, so this f dx function, while its formula looks quite intricate, the core of proving Theorem 1, the big result, seems to boil down to a single, elegant, technical result. Lemma 1, is that right?
That is absolutely correct. Lemma 1 is the linchpin, the mathematical heart of the proof. It states, for fd as above and do2, f dx equals 0 for all x or rd. In plain language, Lemma 1 rigorously proves that f dx is in fact a harmonic function. The entire proof of Theorem 1 then hinges directly on this single lemma. Let's meticulously trace that connection to ensure full clarity. If f dx is indeed harmonic, which Lemma 1 establishes, we then only need to demonstrate that it vanishes specifically on the D2 skeleton of the unit cube QD and is non-zero elsewhere.
Right, because the theorem requires it to be harmonic and 0 on the skeleton.
Precisely. Consider any point x that belongs to an edge E of the D2 skeleton. By the precise definition of the D2 skeleton that we discussed, for such a point x, at least two of its coordinates, let's say xk and xl, where k is not equal to L, must satisfy one of two conditions. Either xk and xl are both equal to 12, or xk is tangential and chortial is 12, meaning they have opposite signs but the same magnitude. In both of these scenarios, sk will be G12, which is 14.
And xul will also be 14.
Yeah.
Exactly. xl will also be 12, so 18, 14. This means that the term x df AO within the product, 1ijo, will evaluate to 14 ixel livro. Since f dx is defined as a product, if even one term in that product is 0, the entire function f dx will be 0, therefore f dx indeed vanishes on the D2 skeleton. Since we've established that f dx is harmonic by Lemma 1, and we've just shown it vanishes on the specified skeleton, it perfectly fulfills all the conditions of Theorem 1, thus solving the Scottish book problem.
So the ingenious design of FDX means that its very structure guarantees it's 0 on those edges because of those XDOJ terms. It's baked right in. And the paper promises two different proofs for Lemma 1, a direct computational one and one leveraging classical Vandermonde polynomial properties. That sounds like a perfect transition into the next part of our deep dive. Before we move to the intricacies of those proofs, there's another significant forward-looking goal of this paper highlighted on page 3, constructing new families of harmonic polynomials that vanish on the same set within the unit ball in Rn for NO4. This ambitious goal is achieved through the sophisticated mathematical concept of harmonic morphisms. Theorem 2 is where these new families are introduced.
Harmonic morphisms, that sounds quite advanced.
It is a powerful concept. Formally, Theorem 2 states, in each space, R2k, K01, there exists irreducible, non-degenerate, quadratic, homogeneous harmonic polynomials that divide infinitely many linearly independent harmonic polynomials. And then for odd dimensions, in each space, R2k plus 1, K03, there exists irreducible, non-degenerate, homogeneous harmonic polynomials that divide infinitely many linearly independent harmonic polynomials.
Okay, lots of terms there. Divides infinitely many. What does that mean?
It means that the specific harmonic polynomial mentioned, the irreducible, non-degenerate, etc. one, is a factor of an infinite number of other harmonic polynomials, and those other polynomials are all linearly independent from each other. Let's quickly recap some of those terms for clarity. Non-degenerate means the polynomial truly depends on all n variables. It's not just using a few of them. Irreducible means it cannot be factored into simpler, non-constant polynomials. Quadratic means its highest degree term is 2. Homogeneous implies that all terms in the polynomial have the same total degree, which is 2 here. And of course, harmonic means its Laplacian is 0. This theorem profoundly extends previous work by Loganov and Molinikova, specifically their work in reference 16, which had focused on dimension 4 using only axially symmetric harmonic functions. This shows a much broader applicability across various dimensions.
And like any truly great research paper, it also leaves us with some intriguing open questions, which is always a hallmark of an active field, isn't it? One question mentioned on pages 3 and 4 really ties back to the core of the paper's initial problem. Given a finite union U of affine lines in RARD, under which condition on U does there exist a non-zero harmonic function f such that fu equals 0?
This question is a very natural and significant extension of the main results on paper. The paper makes an important observation here. Vanishing on an edge, which is fundamentally a line segment of a cube, actually implies vanishing on the entire line that contains that edge.
Ah, so being 0 on a part of the line forces it to be 0 on the whole line.
Yes, and this is not a trivial statement. It relies on a powerful property that harmonic functions possess. They are real analytic functions. To give you an intuition, a real analytic function is one that can be represented locally by a convergent power series, like the infinite series you might see for sin, x or x. This property makes them incredibly smooth and rigid. They have a lot of structure. Because harmonic functions are real analytic, a powerful theorem from real analytic geometry comes into play, often referenced from sources like 8 in the paper. This theorem states that if a real analytic function vanishes on a relatively open subset of an analytic subvariety, Think of a line segment as a relatively open subset of the analytic subvariety that is the entire line. Then the function must vanish on the entire subvariety. So if our f dx is 0 on a segment of an edge, it must be 0 along the entire infinite line containing that edge. Previous work, like reference 9, has already explored particular cases of this question, such as specific linear one-dimensional subspaces or parallel lines in the plane. So some history here too.
All right, so we've got the lay of the land, the main problem, the solution function, f dx, and the central lemma 1 that proves it's harmonic. We've even touched on its extensions and tantalizing open questions. The paper itself then outlines its structure for us. Section 2 for the first proof of lemma 1, Section 3 for the construction of these new families, and Section 4, the appendix, for the second proof and that intriguing planar question we just touched on. And a quick note, the author expresses gratitude to Kislakov and Ioann Vasilyev for their valuable discussions, which is a nice touch, highlighting the collaborative nature of mathematics. Always good to see.
Okay, let's dive into the fascinating nuts and bolts of the first proof of lemma 1, which is detailed in what would be page 4 of the paper. This proof is elegant in its directness and relies on transforming the Laplacian of f dx into a form that is already known to be 0, thanks to a powerful pre-existing property, the classical van der Waals polynomial.
Right, the van der Waals polynomial. You mentioned the resemblance earlier.
Exactly. First, we need to clearly define the classical van der Waals polynomial itself, which is denoted Vy for y-armed. It's given by V, y-r, e, or d. Here, y1, y2, y-r-d represents the coordinates. So for D3, it would be y1, y2, y1, y3, y2, y3, just the differences of the variables.
And how does this classical V relate to our specific f dx function, which uses xdi terms? That seems like the critical link.
That is precisely the key connection, and it's quite clever. Recall our function f dx xioute. If we make a simple, elegant substitution letting a new variable u be equal to x phi I for each I, so y1, x squared, all y2 equal to x squared, and so on, then f dx can be written precisely as v x1, x phi 2, x phi. This substitution allows us to connect the Laplacian of f dx back to known properties of the van der Waals polynomial Vy. It's basically v evaluated at the squares of the x coordinates.
Ah, I see. So f dx is the van der Waals polynomial just with x derives y plugged in for y.
In essence, yes. Now, the paper cites a crucial, powerful property from a previous work, reference 15, lemma 3.1, regarding the van der Waals polynomial V. It states that for any triple of real constants, ABC, the following general identity holds true for all year uy. Y plus I y to d, y plus I1 to 0. Let's meticulously unpack this equation. U denotes the second partial derivative with respect to y, and U denotes the first partial derivative with respect to y. This identity is a deeply fundamental and non-trivial result. It's a powerful relationship that applies to the van der Waals polynomial, essentially stating that V annihilates a broad class of second-order differential operators. It makes them 0.
Okay, so V makes that whole complicated expression equal to 0, regardless of A, B, C.
Yes, for any choice of constants A, B, C. For our specific proof, the author makes a strategic and brilliant choice for these constants. A equals 0, B equals 0, and C equals 12. Let's see what happens when we substitute these values into that general identity. The first summation term, B0 and B0, it just becomes IA1 to D, YIVVY, simplifies dramatically. With B0 and B0, it just becomes I1 to D, YIVY. The second summation term, E or the VVY, with C12 becomes AI1 and D12, AEVY. So the entire identity simplifies to AD1 to D, Y and IVY, plus 12I1 to D, AUAY. To make it even easier to compare with our upcoming Laplacian calculation, we can multiply the entire equation by 2, which is allowed since it's an equation equal to 0. This gives us 2 1 to D, YIVY, plus IA1 to DOVY. This equation holds true for all euro due to the very specific inherent properties of the van der Waals polynomial. This is the precise target form we need to arrive at when we compute the Laplacian of f dx. It's where the magic is going to happen.
Okay, so we have this known identity involving V and its derivatives that equals 0. Now we need to calculate the Laplacian of f dx and show it matches this form somehow.
Precisely. Now let's carefully perform the Laplacian calculation for f dx. Remember, we established that f dx is e x sub 1 x 4d. The Laplacian f dx is defined as the sum of its second partial derivatives with respect to each coordinate, sub a1 to deva x or d x sub. We need to compute each term x or d, x1, x 4d using the chain rule. This is the most intricate part of the derivation, so let's walk through the logic of the steps involved, rather than reading out every symbol.
Please do. The chain rule can get messy.
It can. First, we consider the first partial derivative of vx1 x1 with respect to a single excess. Because v is a function of ex equinly, we apply the chain rule. The derivative with respect to e involves taking the derivative of v with respect to e, its corresponding internal variable, and then multiplying by the derivative of y with respect to xo. So the vx1 becomes v, and the derivative of x with respect to d is just 2x1. So the first derivative is v. This makes sense intuitively. The rate of change of v with respect to gis depends on how v changes with y, which is x1, and how y changes with gis.
Okay, first derivative down, now the second one.
Right. Next, for the second partial derivative, xrd by 7(1)xrd, we need to differentiate the previous result, xr with respect to z again. Here, we apply the product rule of differentiation because we have two things multiplied together that both depend on a zeta. The product rule states that the derivative of u, y, u plus, in our case uz, e, and ue. Now, when we differentiate u, which is eze, with respect to z, we apply the chain rule again, because av itself implicitly depends on is, ye, he, sorai. So the derivative of, with respect to z, is g. Using the chain rule, this becomes a e, which is ezc, so uz is xe, and the derivative of v, which is these e with respect to c, is simply v2.
Okay, got the pieces u, v, u.
Exactly. Putting it all together with a product rule, uv plus uv, uv hubiabicia, which simplifies to 4 by 2 uv is duive, which is 2 yurdas. So the second partial derivative uv evobft gem results in the sum of these two terms, 4 by ev plus 2 euro. This is the form of the second partial derivative for a single coordinate phi.
Wow, okay, that's the second derivative for one variable irda.
Correct. Finally, the full Laplacian FEA dx is the sum of these terms over all I from 1 to d. So fbx, 1 to d, 4 by kk, right OB, plus 2 vak. We can separate this sum into two distinct sums, 4aba to d xy plus 2 fe ire. Now, here's the truly pivotal step where everything connects. Remember that in these derivatives, y is just a symbolic placeholder that we defined as xaa. So the derivatives ea and year a are effectively evaluating the derivatives of v with respect to its ith argument, evaluated at the point x0, xda. Look closely at the final expression we derive for af dx, 4a1 to d xaa, plus 2aoa to d. Now compare this with the Vandermonde identity we meticulously simplified earlier. After setting a 0 way, b0, c12, and multiplying by 2, feoa plus a bay plus a way, if we factor out a 2 from our calculated Laplacian expression, we get 2a01 to d xea plus av to d. When we substitute y x dasni back into the Vandermonde identity, the expression inside the square brackets in our Laplacian calculation exactly matches the Vandermonde identity we know is equal to 0. It's a perfect match.
And just like that, we beautifully see f dx equals 2, 0 is 0 equals 0, meaning f(e) is indeed a harmonic function. That's a truly elegant piece of mathematical reasoning, seeing how those intricate terms from the chain and product rules, initially looking so complex, perfectly cancel out due to the underlying power and symmetry inherent in the Vandermonde polynomial. The genius here lies in recognizing that connection and choosing the right constants a, b, c.
It truly is a remarkable demonstration of how deep mathematical properties can simplify seemingly complex problems. This direct computational proof, while requiring meticulous application of the chain rule, ultimately hinges on that powerful pre-existing identity for the Vandermonde polynomial. The aha moment is realizing that the Laplacian of f dx is simply a scalar multiple of a known identity that evaluates to 0.
Now, the paper briefly mentions a second proof for lemma 1 tucked away in the appendix. It hints at leveraging the fact that the classical Vandermonde polynomial is harmonic and annihilates certain general second-order differential operators. What does it mean for a polynomial to annihilate an operator in this context?
To annihilate an operator is a more abstract but powerful concept in mathematics. It simply means that when you apply that specific differential operator, like the Laplacian or something more general, to the function or polynomial in question, the result is 0. It's like the operator destroys the function, reducing it to nothing. So in this context, it implies that there exists certain second-order differential operators, which are more general than just the Laplacian, that when applied to the classical Vandermonde polynomial Vy, yield 0. This second proof, as referenced in 15, would likely involve showing that the Laplacian, when applied to our f dx, which is v evaluated at x bay, can be cleverly transformed or related to one of these more general operators that the Vandermonde polynomial Vy is known to annihilate. This approach relies on a higher-level mathematical insight and a theory of such operators, rather than direct brute force computation of derivatives. It showcases the versatility and interconnectedness of different mathematical approaches to the same problem.
All right, let's transition now to section 3 of the paper, which tackles an exciting problem: how to construct entirely new families of harmonic polynomials. This is where proposition 1 comes in, discussing how to generate many different harmonic functions that can share the same zero set, especially within a small region like a ball.
Yes, Proposition 1 is a cornerstone for understanding how the paper extends its results beyond just a single function like f dx. It establishes the precise conditions under which we can create infinite, linearly independent families of harmonic functions that are guaranteed to share a common zero set, at least locally within a defined region. The proposition states, let fj1 be a linear independent family of functions satisfying fjhrn with na3 for each j, and such that there exists zero satisfying z of jb0, e of ab0 of s for all ijnn, and let faf rm arn be any non-constant harmonic morphism.
Okay, let's break that down. Fj1 is just an infinite sequence of functions, f1, f2.
Right, an infinite sequence. The crucial property here is that they must be linearly independent. This means that no function in this entire family can be expressed as a linear combination of the others. They're fundamentally distinct. Each fj must also be harmonic in Rn for NO3. That's our base requirement. The condition zfj ab0 equals f ab0 is absolutely key. Zf denotes the zero set of f, meaning all the points x where fx equals 0. B0 day is an open ball of radius a centered at the origin, just a small sphere around the center point. So this condition means that all these initial functions fj must have the exact same zero set within that small ball around the origin. It's like they all vanish on the same particular pattern near the center.
They all agree on where they are zero, near the origin. Makes sense. And the last piece, the harmonic morphism.
Yes, the final and perhaps most sophisticated element is Savam RR which must be a non-constant harmonic morphism. What exactly is a harmonic morphism? In essence, it's a very special type of mapping or transformation between two spaces, in our case Euclidean spaces, Rm and Rn. It has a profound and incredibly useful property. It pulls back harmonic functions to harmonic functions. This means if you have a harmonic function h defined on the target space Rn, and you apply the mapping to the input of h, i.e. you form the composition ha, meaning Zebay's x, the resulting function on the source space Rn will also be harmonic. This is an incredibly powerful concept in geometry and analysis because it allows mathematicians to transfer the property of harmonicity across different spaces in a predictable way.
So it preserves harmonicity when you compose functions with it?
Cool. Exactly. Given these precise conditions, linearly independent harmonic functions sharing a local zero set and a non-constant harmonic morphism. Proposition 1 leads to three significant conclusions. 1. V fjr for all jn. This means that if you compose the harmonic morphism with any of our initial harmonic functions fj, the resulting composed function pjx is itself harmonic. This is pretty much evident from the definition of a harmonic morphism itself. 2. Fichte is a linearly independent family. This means the newly composed functions also form a linearly independent family. This is not immediately obvious, and it's a key strength of the proposition. 3. There is z-phi 0, such that Zophi AEB01 equals Zphi B011. This implies that the composed functions phi sjAEJ will also share the exact same zero set and a potentially smaller, but still non-empty, ball around the origin. Again, this follows naturally from how harmonic morphisms transform zero sets.
So the morphism preserves harmonicity, linear independence, and the shared local zero set property.
Precisely. The proof breakdown for these conclusions is remarkably concise, reflecting the established theory of harmonic morphisms. Points 1 and 3, preserving harmonicity and the local zero set are indeed considered evident due to the very definition of a harmonic morphism and the straightforward way zero sets transform under such a mapping. The most interesting part of the proof and the non-trivial aspect is point 2, establishing the linear independence of the new family. This relies on a powerful result from classical analysis, referenced as 1 in the paper, which states that if CR Rn is a non-constant harmonic morphism, then it must be surjective.
Surjective, meaning it hits every point in the target space Rn.
Exactly. Surjectivity means that every point in the target space Rn is mapped to by at least one point from the source space. The mapping covers the entire target space. When a mapping is surjective, it fundamentally preserves linear independence. If your initial family is linearly independent and maps Rm onto Rn, then any linear combination of the composed functions that evaluates to 0 would imply a linear combination of the original fj functions was 0.
because it covers the entire target space. So if the composition is 0 everywhere, the original functions must have been 0 in a way that contradicts their independence. This would directly contradict the initial assumption that was linearly independent. This ensures that the newly generated family retains its distinctness.
Okay, that makes sense. Surjectivity is key there.
Yes. With this foundational understanding of proposition 1 and harmonic morphisms, we can now move to the crucial part, the actual proof of theorem 2, which applies these concepts to construct those new families of harmonic polynomials. Let's begin with the case of even dimensions, specifically R2n, where k are 1. The paper introduces a very specific and elegant mapping R2n. This mapping takes a point x 1 by 1 by 2n from the two-dimensional space and maps it to a pair of values in R2. The components are defined as kr 2x, x12 plus x4 plus cr plus xx 2n 1 more plus x6 2 under alternating signs of squares and do x 2 by 1 by 2 plus 2 by 3 by 4 plus n plus 2 by 2 and here twice the product of consecutive pairs. The paper directly states that, according to a known result from reference 21, Theorem 5.1, this specific mapping is a harmonic morphism. This is a pre-established and powerful result from the specialized theory of harmonic morphisms that the author leverages. We don't need to prove it here. We can take it as given from that source.
Okay, so that specific is our harmonic morphism for even dimensions, and the paper then makes a very strong claim. 1x, the first component, is an irreducible, non-degenerate, quadratic, homogeneous harmonic polynomial. That's a serious mouthful of mathematical adjectives. Let's just briefly recap what each of those terms signifies to ensure we're all on the same page.
Absolutely. Let's break down each term again for clarity in this context. Irreducible. This means 1x cannot be factored into a product of 2 or more simpler non-constant polynomials over the real numbers. You can't break x0 plus 8 down further easily. Non-degenerate. As we discussed, this means the polynomial genuinely depends on all its variables. For 1x, you can clearly see by 1 through by 2n are all present and contribute to its definition, confirming its non-degeneracy, assuming n1. Quadratic. This refers to the highest degree of the terms in the polynomial. All terms in 1x are of degree 2, like x0 covariant, making it a quadratic polynomial. Homogeneous. This means all terms in the polynomial have the exact same total degree. Here, every term sinuses as a total degree of 2, so it's a homogeneous polynomial. Harmonic. And of course, this is the core property. Its Laplacian error when x is guaranteed to be equal to 0. This property is inherent to 1 being a component of a harmonic morphism mapping to R1.
Got it. So 1 has all these nice properties. How does it divide infinitely many linearly independent harmonic polynomials? Where do the infinite families come from?
Right. So given that 1x possesses all these properties and is part of a harmonic morphism, 1, 2, 2, how does the paper use it to generate these families? The paper provides a brilliant example. Consider the complex valued function formed by zx plus I2x. Since RE12 is a harmonic morphism from R2 into R2, which we can identify with the complex plane C, the zx effectively behaves like a complex analytic function, or more precisely, constitutes what's called a minimal generalized Cauchy-Riemann system. A fundamental property in complex analysis is that integer powers of complex analytic functions, like zx for any positive integer m, are also complex analytic or satisfy similar properties. And as we established earlier, the real and imaginary parts of any complex analytic function are themselves harmonic. Therefore, the paper suggests looking at, for example, zz second 2k, the imaginary part of zx, raised to the power 2k for any natural number k. This will always be a harmonic function, a polynomial in fact. By simply varying the integer k, UZL k1, 2, 3, you can generate an infinite number of distinct, linearly independent harmonic polynomials.
Crucially, because z derivative 2k, 1 plus I2 2k, if 1x 0, then z by 2k, I2k, I2k, 2k, minus 1k, 22k. The imaginary part of this is 0. So any point where 1x 0 is automatically a 0 for z by 2k. This means 1x is a factor of, or divides, all these infinitely many harmonic polynomials, e back 2k. This significantly expands and generalizes the results from earlier works like Loganov and Melendikova in reference 16.
Wow, that's really clever how they use complex powers to generate the infinite family, and how 1 being 0 forces the imaginary part to be 0 too.
A very elegant construction. Now let's turn our attention to the intriguing case of odd dimensions. The paper considers m as 2k plus 1 with ko2, which implies mo5. It references a specific construction from example 5.2.7 in a comprehensive text, reference 4. This reference provides a general form for a harmonic morphism. phi1x for arm to C, which again is the complex plane, or R2. The core structure of this mapping involves terms like opal1 plus x xam plus x xa1, or x phi1 plus xm, and the coefficients x ked depend on z x xm plus x. This mapping is proven to be a harmonic morphism provided that a very specific and crucial condition holds. The sum of the squares of the coefficient functions xa must identically be 0 for all s, that is, xam poly j is 0. This is the mathematical constraint that needs to be satisfied for text A1 to be a harmonic morphism in this odd-dimensional setup.
Okay, a sum of squares equaling 0. That sounds restrictive. How can that happen unless all the terms are 0? Especially if they are functions.
That's the clever part. It can happen if some of the Auger functions are complex valued, specifically involving the imaginary unit I. The paper points to a powerful technique called ansatz 6.8.6 in reference 4. An ansatz in mathematics is like an educated guess, or a proposed form for a solution that simplifies a problem. This ansatz provides a specific form for the component functions, layoffs and polynomial that guarantees the sum of their squares is 0. The form involves components like 1 I1 plus G, and negative GA will go as shorthand for G1 plus 2 into the sum of squares of some chosen polynomials, Gj, and G1 represents any arbitrary choice of polynomials for these Gj.
So I is involved. That must be how the squares can cancel to 0.
Exactly. Let's quickly demonstrate the logic of how this works, without getting lost in the full algebraic expansion. Imagine for simplicity that M2, 3, so we had idero 1, 2, velocity 3. Let idero 1, 1, 1 joule, 1 into 2 is I1 plus 2 joule, where idero is idero 2 velocity G, where G is now just a single polynomial G1. Our goal is to show that ideros plus ideros plus idero plus uteros ideros 1 1 plus G. Idero plus mega plus T. Idero plus Q in these studio orders like negative 1 is loaded. Play use post 0 as the native studio pulled before. Now add them up. 1 where 0 double to flow plus negative 1 2 make what is plus 4 0. The 1 and 1 equals 4. Now we're left with next to it a 2 rego is 0 cancel. And we're left with minus 2 w total go ahead plus 4g will do go to 0. So the terms are designed to perfectly cancel each other out, thanks crucially to that Eiger's wording more apply. This is the crucial step to show the condition in EU is met. This confirms that Q and Romeo 2 indeed acts as a harmonic morphism for these odd dimensions for method rule 5.
Once we have this, we can replace 1, 2 from our even dimensional considerations with phi 1, 2, and apply the same reasoning, using powers of phi 1 plus I phi, to generate infinite families of harmonic polynomials in odd dimensions where phi 1 divides all the imaginary parts.
That's brilliant how the complex number makes that cancellation possible.
It is. The paper adds some important remarks regarding the specific dimensions for this odd case. While this argument for AOM4 technically holds for all AMEO3, which corresponds to K1, the paper notes that it gives no non-trivial example that we wish to construct. It just doesn't yield the kind of complex non-trivial functions we're looking for in that lowest odd dimension. And for MEO4, which of course is an even dimension, that case was already fully covered by the construction we discussed earlier. So the restriction to MEO5 is specifically for generating new, non-trivial examples of these families in odd dimensions not previously addressed.
Fascinating. And the paper even mentions other types of harmonic morphisms, like Hopf polynomials, which sound intriguing as well. It's clear this field is rich with many different ways to construct and understand these functions, pushing the boundaries of what's possible. Now we'll move into section 4, the appendix, which brings us back to that intriguing open question we mentioned earlier. What specific kinds of unions of affine lines can actually serve as nodal sets for non-zero harmonic functions in the plane?
All right, this is a challenging question that requires sophisticated tools. The paper explains that thanks to a very powerful mathematical tool called the Schwartz reflection principle for harmonic functions, which is referenced in standard texts like reference 3, the problem can be significantly simplified. The Schwartz reflection principle is a truly remarkable theorem. It states that if a harmonic function vanishes on a portion of a straight line, or more generally, a smooth analytic boundary arc, then under certain conditions, you can analytically continue or extend that function across the line by reflecting it. It's like using the line as a mirror to define the function on the other side, and the amazing thing is, the extended function remains harmonic.
So you can extend the function across lines where it's 0.
Essentially, yes, under the right conditions. This principle is incredibly useful for constructing or understanding harmonic functions in more complex domains, often by piecing together simpler solutions or extending known ones. Applying this powerful principle, the paper asserts that for a finite union of lines in the plane, the only case truly needing detailed treatment where a non-zero harmonic function might exist that vanishes on them is a union of 3 lines, where 2 are parallel and the third intersects them. All other simple arrangements of lines either trivially imply the function is zero, due to principles like the maximum principle we discussed if they form a closed boundary, or can be handled by simpler extensions or arguments. The paper then performs a critical case analysis on this three-line setup. If the third line is not orthogonal, not at a 90-degree angle to the parallel lines, then any harmonic function vanishing on this union must be zero identically. Why is that? The reasoning for this is described as easy geometric observations coupled with one more application of the Schwartz reflection principle. What this implies conceptually is that through successive repeated reflections of the zero set across these non-orthogonal lines, the zero set of the function would effectively become dense in the plane. Imagine reflecting across slanted lines. The reflected lines will cross each other at various angles, eventually filling up the plane. And as we established earlier with the maximum principle and related uniqueness theorems, if a harmonic function is zero on a dense set meaning points where its zero are arbitrarily close to every other point, then the function is forced to be identically zero everywhere.
The reflections fill everything up if the lines aren't orthogonal.
Exactly. This critical insight means we can specifically focus on the scenario where the three lines in question form an orthogonal half strip, as this is the only configuration among simple unions of lines that can support a non-zero harmonic function. An orthogonal half strip is formally defined as h by 1 by 2, 0 by 2 by 2. This describes a rectangular region in the Cartesian plane, bounded below by the x-axis segment from -2 to 2, where by 2, 0, and bounded on the sides by the vertical lines by 1 of 2 to power 2 and by 1 equals 2, and then extending infinitely upwards in the positive by 2 direction. This is the precise domain where a non-trivial solution can exist.
So for this very specific orthogonal half strip, the paper actually provides an explicit, exact formula for a non-zero harmonic function that vanishes precisely on its boundary. I recall that it looked incredibly complex when we looked at the outline, given as Formula 1 in the paper.
It is indeed a beautifully complex formula, showcasing the intricate nature of these solutions. The function s0 by 1 by 2 is given by a daunting-looking combination of trigonometric, sin cos, and hyperbolic sin cos functions. It includes terms like cos by 1, sin by 2, square roots involving sin by 1 plus sin cos 2, and even reciprocals of similar terms. This isn't a formula one could guess. It's the result of deep mathematical work, often using sophisticated techniques like conformal mappings, as we'll touch on.
Right, and verifying it works. The paper calls it routine.
Well, routine for a mathematician perhaps, but definitely non-trivial. To check its harmonicity, you would need to calculate its Laplacian, S-euro plus euro zero, and painstakingly demonstrate that it equals zero for all points inside the half strip. This would involve a significant amount of partial differentiation using chain rules, product rules, quotient rules, and very careful algebraic manipulation of trig and hyperbolic identities. It would be quite lengthy. To check if it vanishes at the boundary, you would substitute the boundary conditions into the formula by 1 equals 2, by 1 equals 2, by 1 up 1, and by 2 equals 0. For example, if by 1 equals 2 and now is a 2, then cos by 1 would be 0. Since cos by 1 is a direct multiplicative factor near the front of the formula, this makes the entire function s0, 0 on those vertical boundary lines. Similarly, if by 2 equals 0, then sin by 2 would be sin 0, 0, 0. Since sin by 2 is also a key multiplicative factor, this makes is0, 0 on the horizontal boundary segment s0, 0 between -2 and 2, so it does meticulously vanish on the specified boundaries.
And the paper even provides us with a visual, figure 2, showing a blue graph of S0, so we can actually see this incredibly intricate function's behavior, which is so helpful for something so abstract. How would mathematicians even begin to discover such a complex, exact formula? It seems like it would be impossible to just stumble upon it.
You're absolutely right. It's certainly not a matter of guesswork. The discovery method, as the paper subtly alludes to on page 7, involves leveraging other powerful mathematical tools, most notably conformal mappings. Conformal mappings are transformations that preserve angles locally. They are extraordinarily useful in complex analysis and harmonic function theory because they possess this magical ability to map a complicated geometric domain to a simpler one, like a half-plane or a disk, while precisely preserving the property of harmonicity.
So you map the hard shape to an easy shape.
Exactly. For instance, the paper mentions xpb1 sin by 2, which is the imaginary part of SPB, as a well-known harmonic function that is 0 on the boundary of an entire infinite strip, like 0 by 2. Another simple example harmonic in a strip is sin by 1, sin by 2. The ingenious idea is that you start with a simpler known harmonic function on a simpler domain where its zero set is well understood, like the upper half plane or a simple strip. Then you find a conformal mapping that carefully transforms that simpler domain into the more complex domain you're interested in, such as our half-strip H. This sophisticated process transforms the function and its zero set in a predictable and controlled way. If the original function was 0 on the boundary of the simple domain, the transform function will be 0 on the transformed boundary, which is the boundary of our target domain H. This allows the construction of these seemingly impossible explicit formulas like F0.
That's a truly clever strategy. Transform the problem, solve it in the easy space, then transform back. Okay, now the paper shifts gears again, moving to 3D with Proposition 2, which looks at zero sets on the boundary of a prism.
Yes, Proposition 2, found on page 8, extends the problem to 3 dimensions, specifically focusing on certain types of prisms. Let's meticulously define the geometric components involved, WASAEL, LAO, like it's by 0. This is simply the YZ plane, the coordinate plane where the first coordinate is 0, PDEs 0. This denotes a bounded triangle that is located within that YZ plane. It's a flat, two-dimensional shape lying in that plane. CP, EOXVAS plus EO1 where V is ER. This defines a two-sided, unbounded prism. Imagine taking our triangle P in the Y plane and extending it infinitely in both the positive and negative by 1 directions, parallel to the by 1 axis. Here, E1 is the unit vector, 1000, pointing along the by 1 axis. So CP is essentially a cylindrical prism with a triangle P serving as its constant cross-section.
Like an infinitely long Toblerone box if P was a triangle.
Exactly like that. Proposition 2 then delivers 2 incredibly powerful statements about these infinite triangular prisms. 1. For most triangles, non-conformal tiling. If the triangle P is not one of 4 very specific types of triangles, specifically those with angles, 60 degrees is 60 degrees is 60 degrees, which is equilateral, 30 degrees, 30,120 degrees, 40 degrees, 60 degrees, 90 degrees, which is a standard right triangle, or 45 degrees, 90 degrees, which is an isosceles right triangle, then for any function of Friese that is harmonic in on, if phi vanishes on the entire boundary of the prism U or CP, it implies that phos must be identically 0 everywhere.
So for most triangle shapes, the prism boundary is a uniqueness set.
Correct. For most triangles, their corresponding infinite prisms cannot support a non-zero harmonic function that vanishes on their boundaries. 2. For special triangles, conformal tiling. Conversely, if P is one of those 4 specific types of triangles, then a non-zero harmonic function, fold Nancy HR, does exist that vanishes precisely at the boundary of CP. This is the exciting part, showing that such non-trivial solutions are possible for these special geometric cases.
Why those 4 specific triangles? What's special about them?
That's the key question. Let's briefly walk through the logic of the proof sketch provided for statement 2, which shows the existence of a non-trivial function. It begins by citing reference 10, Gardner's work, which establishes the initial existence of a non-zero harmonic function, S0, defined within the prism CP itself, and vanishing on its boundary euro. The critical next step is extending this F0 to the entire space R. This is again achieved using the robust Schwartz reflection principle we discussed earlier, reflecting across the flat faces of the prism. What's absolutely crucial here is the unique geometric property of these 4 specific types of triangles, PO mentioned in statement 2. Their successive reflections with respect to sides never self-intersect and form a tiling of the whole plane.
They tiled the plane, like bathroom tiles.
Exactly. If you take one of these special triangles, equilateral, 30, 60, 90, etc., and reflect it repeatedly across its edges, they perfectly fit together without any overlaps or gaps, completely covering the plane W. This remarkable tiling property is key. Because the reflections don't overlap, it allows for a consistent analytic extension of the function S0 across the boundary faces through an infinite sequence of reflections. Critically, because the zero set formed by these reflected boundary faces tiles the entire plane W, and thus the boundaries tile R, without becoming dense in a way that forces the function to be 0 everywhere, the non-triviality of the function is preserved. The zero set remains structured.
So the tiling prevents the zero set from becoming too dense.
Precisely. For the proof of statement 1, the contrary case, where P is not one of those special tiling triangles, the paper refers to reference 5 by Barney, Frankel, and Maihara. In this scenario, if P is not one of those special triangles, then the corresponding sequences of reflections of P are dense in Aragon. This means that if you repeatedly reflect such a non-special triangle P across its sides, these reflections will overlap and eventually cover the plane W in such a way that the boundary segments become arbitrarily close to every point in the plane. Consequently, the zero set of Fing would effectively become dense in RO, and thus within the Hanoan extended prism boundary in RO. And as we've consistently established, the harmonic function that is 0 on a dense set must be identically 0 everywhere. This highlights again how the fundamental geometry of the zero set directly dictates the global behavior of the harmonic function.
So it all comes back to how the zero set spreads through reflections. If it gets dense in a certain way, the function has to be zero everywhere. The tiling property is the escape route. The paper then wraps up with some more remarks and insightful open questions. For the second statement of Proposition 2, where P is one of those special triangles, the paper notes that if P is specifically the unit square, which can be made by two 45, 45, 90 triangles, an explicit function already exists thanks to Lagunov and Molinikova from reference 16.
Yes, this is a beautiful and important example because it provides a concrete, explicit formula for such a function, this time for a prism with a square base or cross-section. The function T-trox is given by sin 1 by fin, sin 1 cried. The crucial condition for this function to be harmonic is a relationship between the constants a plus aed plus any1. This ensures the Laplacian cancels out.
So D3, it would be sin euro with a piasca I plus...
Exactly. Let's briefly explain the logic of why this function is harmonic and vanishes on the boundary of the corresponding prism. Let's assume the prism is aligned with the axis. To verify it's harmonic, one would compute its Laplacian. When you compute the second partial derivative with respect to each coordinate xk, for k from 1 to d1, the sin xk term, when differentiated twice, brings out a factor of lexo. For the last coordinate xd, the sin xd term, when differentiated twice, brings out a factor of plus egas. When you sum all these second partial derivatives to form the Laplacian, the condition xk equals ac1 plus xk ensures that the sum of the negative x-act terms from the signs perfectly cancels out the positive act term from the sin function, making the total Laplacian 0. It's a neat cancellation.
And it's 0 on the boundary because of the signs and...
Precisely. It's also quite clear that MEX evaluates to 0 at the boundary of the corresponding prism, say defined by xk0 or xk soc for kd and xe0. If, for instance, any x I found from 1 to d1 is such that sin I well and becomes 0, for example, if xe equals 0 or y I, then the entire product x will be 0 because it has a factor of 0. Similarly, if xd equals 0, then sin ix would be sin 0, 0, again forcing the x to be 0. So this function indeed vanishes precisely on the boundary faces of the prism defined by these coordinates. It's a very elegant construction for the square rectangular prism case.
And this paper, like any truly great piece of research, leaves us with even more to ponder, which is the sign of a vibrant field.
Absolutely. The paper concludes by pointing towards further open questions, pushing the boundaries of this fascinating research. One key question is explicitly stated. It would be interesting to find out if such explicit formulas exist in the case of other p, as in 2, and in case of several dimensions. We've seen an explicit formula for the unit square prism, but can we write down similar exact functions for the prisms based on the other three special triangles, equilateral 30, 30, 120, 30, 60, 90, or for similar structures at higher dimensions? That's a significant challenge. Finding explicit formulas is often much harder than proving existence.
Right. Existence is one thing, writing it down is another.
Exactly. Another deeply intriguing open question mentioned is to classify all non-zero harmonic functions that vanish on the boundary of a half strip or a half prism. We've seen one such complex function for the half strip, that S0 by 1 by 2, but how many are there? Are there other families, perhaps simpler ones, or ones with entirely different properties? This calls for a complete characterization, a comprehensive understanding, which is a much more profound problem than merely finding a single example. These questions beautifully highlight the ongoing dynamic nature of mathematical research, where each solution often opens up new, compelling avenues for exploration, inviting future generations of mathematicians to continue the deep dive. #tagoutro.
So what does this all mean? We've journeyed from a 1936 problem in the legendary Scottish book, with its playful fondue prize, to elegant modern solutions involving these intricate harmonic functions. We've seen how FDX, a function beautifully constructed from a product of xi, xj terms, elegantly and surprisingly solves the problem of finding a non-zero harmonic function that vanishes precisely on the edges of a cube in 3D and higher dimensions. Quite something.
We meticulously walk through the conceptual derivations, gaining a deeper understanding of how the chain rule transforms complex expressions and how the known, profound properties of Vandermonde polynomials are ingeniously applied to prove that FDX is indeed harmonic. That connection was key. We also explored the fascinating and powerful concept of harmonic morphisms, which are truly remarkable mathematical tools. They allow mathematicians to generate entire families of complex functions that all share the same intricate zero sets, pushing the very boundaries of what was previously known about these functions.
Yeah, those harmonic morphisms were quite a concept. And we saw how classical tools like the ingenious Schwartz reflection principle, when combined with modern insights into geometric tiling and the behavior of dense sets, are still absolutely vital in understanding and constructing these functions. It really demonstrates that fundamental mathematical principles continue to yield surprising and beautiful new results in unexpected ways. Old tools, new tricks.
Absolutely. This deep dive into Ioann Vasilyev's paper highlights that even in highly specialized fields like harmonic analysis, there are profound and unexpected connections between seemingly disparate concepts. From the fundamental geometry of a cube to the abstract algebra of polynomials and the elegance of complex analysis. It all ties together. It leaves us with a truly important question, I think. What other long-standing mathematical problems, which currently seem entirely out of reach, might ultimately be solved by unexpected connections between different, perhaps even distant, branches of mathematics? Where else might these bridges exist?
That's a great question to ponder. We truly encourage you, our listeners, to revisit the concepts we discussed today. Perhaps look up the intuitive definitions of harmonic morphisms, or delve deeper into the surprising properties of Vandermonde polynomials or those tiling triangles. The beauty in mathematics is often in the details, and the deeper you look, the more interesting and interconnected it gets. Until next time, keep that incredible curiosity alive.
Okay, let's unpack this. Imagine you're standing before a puzzle that has genuinely stumped some of the brightest minds in mathematics for nearly a century.
Yeah, it's quite something.
It's a seemingly simple question, really, about where certain fundamental mathematical functions, known as harmonic functions, can simply vanish, meaning equal zero, without the function itself being completely trivial or, zero everywhere.
Right. That distinction is crucial. Not just zero, but non-trivially zero on some set.
Exactly. Today we're taking a deep dive into a truly fascinating paper titled On the Zero Sets of Harmonic Polynomials. This isn't just about solving a decades-old enigma. This paper actually provides a positive solution to that exact challenge. And in doing so, it illuminates exciting new pathways for us to understand these functions in much broader, more profound context.
It really does open things up.
We've got a rich, detailed document in front of us, filled with elegant mathematical notation, intricate derivations, and rigorous proofs.
It's dense, but incredibly rewarding.
Our mission today is to meticulously break it down for you, section by section, concept by concept, and pull out the most important insights, making even the most complex ideas crystal clear.
What's truly compelling here is how this paper approaches a classical domain of mathematics specifically, potential theory, but it does so with incredibly fresh, modern tools and insights.
So old problems, new tricks.
Kind of, yeah. We'll be navigating through some very precise mathematical definitions. Concepts like what makes a function harmonic or what properties a set must have to be considered a uniqueness set are the absolute bedrock upon which solutions to these significant, intricate problems are built.
Right. The foundations need to be solid.
Absolutely. Our goal is to go beyond just stating the findings. We'll want to thoroughly understand the mathematical reasoning behind each conclusion, to trace every single derivation step, rigorously defining each term as we encounter it, and walking through the processes with granular step-by-step explanations.
Sentence by sentence if need be.
Pretty much, yeah. By the time we wrap up this deep dive, you'll not only have a clear grasp of a surprising answer to a very old problem, but you'll also get a first-hand look at the ingenious ways mathematicians construct, analyze, and ultimately conquer these wonderfully complex functions from the ground up.
So let's begin right where the paper does at the very beginning by introducing its core subject, the harmonic function. The paper immediately tells us what it means for a function to be harmonic. What exactly does that entail, and why is the concept of its Laplacian being equal to zero such a critical part of its definition?
That's the perfect place to start, because truly grasping this fundamental definition unlocks everything that follows. A function, let's denote it as f, is considered harmonic within a particular region of space, what mathematicians call a domain, which we'll represent as f in rad, our d-dimensional space, if its Laplacian, which is formally denoted by f, is equal to zero everywhere within that specific domain.
Okay, so the condition is f equals 0?
That's the defining condition, yes, f equals 0.
And this Laplacian operator sounds like something straight out of advanced physics. What is it, precisely?
Hey, it does pop up there a lot, but it's fundamentally a mathematical operator. We represent it with the symbol a, Formally, it's defined as the sum of second-order partial derivatives with respect to each coordinate. So in mathematical notation, we write it as AR, KR1, error is in UK2.
Whoa, okay, let's break that down. Error is sum, right?
Right. The capital sigma means sum. And AOSR ACO2, that signifies a second-order partial derivative with respect to a single coordinate, ARCO.
Partial derivative. That means you treat the other variables like constants when you differentiate.
Exactly. If your function depends on, say, by 1, by 2, and by 3, the partial derivative with respect to y1 just looks at how the function changes as by 1 changes, holding by 2 and by 3 fixed.
And second order means you do that twice.
You got it. Differentiate once, then differentiate the result again, with respect to the same variable xk. The Laplacian then just sums up these double differentiations for all the coordinates in your space, from k1 to d.
Okay, so sum of double partial derivatives for every dimension. What does that mean intuitively?
Conceptually, the Laplacian provides a measure of how much the value of a function at a specific point deviates from the average of its values in its immediate surroundings.
Like, is it higher or lower than its neighbors on average?
Precisely. Think of it as a way to quantify smoothness, or maybe flatness in a certain sense. When the Laplacian of a function is 0, which is the hallmark of a harmonic function, it means the function is in a state of perfect balance at that point.
No big bumps or dips compared to the average around it.
Exactly. There are no sources or sinks within the domain where the function is, say, mysteriously increasing or decreasing faster than its surroundings would suggest. It implies there are no points where the function's value is either significantly pulling away from or collapsing towards the average of its neighbors. It's in a kind of equilibrium.
Okay, that makes sense. And the paper defines HA.
Right. HA is just the set or the collection of all such harmonic functions within that given domain. And importantly, for the main part of this paper, we'll mostly be considering HRD, which means functions that are harmonic across the entire d-dimensional space, unless, the text explicitly says otherwise.
So if a function possesses this unique balanced property, this harmonicity, what happens if its value is 0, it vanishes, on a particular set of points within its domain? Does that tell us anything more about the nature of the function itself?
Yes. That line of questioning leads us directly to another critical concept introduced early in the paper, the uniqueness set.
Uniqueness set, okay.
A subset S of our domain, so SA, is termed a uniqueness set for the space of harmonic functions, HA, if the following condition holds. For any function f that belongs to HA, meaning f is harmonic in A, if f is 0 on S, which we denote as fs is 0, then it necessarily implies that f must be 0 everywhere throughout the entire domain. So fx equals 0 for all x in A.
Wow. So it's a very specific collection of points that holds so much mathematical sway that if a harmonic function happens to be 0 on them, it's essentially forced into being 0 everywhere else.
Yeah.
That's a powerful constraint.
It's incredibly powerful. And the paper is quick to point out that there are certain trivial cases where this outcome is immediately apparent.
Like what?
Well, for instance, if a harmonic function vanishes on an open set, and by open set we mean any region, no matter how small, that contains only its interior points without including its boundary, like a little disc or ball without its edge.
Okay.
Or if it vanishes on a closed rectifiable curve, essentially, a continuous curve with finite length that closes back on itself like a circle or an ellipse,
Right.
then that function is trivially 0. It has to be 0 everywhere.
And why is that trivial?
It isn't a deep mystery or a complex proof. It's a direct and fundamental consequence of what's called the maximum principle for harmonic functions.
The maximum principle again. You mentioned that briefly. What does it tell us?
Intuitively, the maximum principle for harmonic functions states that a non-constant harmonic function cannot achieve its maximum or minimum value inside its domain.
Only on the edges.
Exactly. Any extreme values must occur only on its boundary. This property makes harmonic functions incredibly constrained, very well behaved in a sense. So if a harmonic function is 0 across an entire open set, even a tiny one, it would violate this maximum principle unless the function itself was 0 everywhere.
How so?
Because if it were non-zero somewhere else, it would have to somehow rise up from 0 inside that open set, reach a maximum or minimum, and then fall back to 0 within that open set, which the principle strictly forbids for non-constant functions.
I see. So it can't have peaks or valleys inside the region, only on the border. So being 0 on an open set forces it to be flat 0 everywhere.
Precisely. Thus, for such common sets, the uniqueness property is straightforward.
So the really intriguing uniqueness sets are the ones where it's not immediately obvious that vanishing on a specific set forces the function to be 0 everywhere. These would be the non-trivial challenges, right?
Exactly right. And the paper makes a significant statement here, highlighting the immense complexity of the field by noting that a general, comprehensive description of all uniqueness sets for HRD is currently considered out of reach.
Wow. So we just don't know how to characterize them all.
Not even close, apparently. It signifies an incredibly difficult, perhaps even intractable, problem in its full generality. The paper emphasizes this difficulty by adding that it remains challenging even when mathematicians constrain their focus to seemingly simpler scenarios, such as finite unions of affine subspaces.
Affine subspaces.
Yeah.
What are those again? Like lines and planes?
Yeah. Basically, yes. An affine subspace is essentially a generalized line, plane, or hyperplane that doesn't necessarily pass through the origin. It's a geometric concept that extends linear spaces. Think of a plane shifted away from the origin. The fact that even characterizing uniqueness sets made of finite unions of these relatively simple geometric objects is problematic underscores the depth of the challenge.
Okay, so the general case is clearly a monumental task. But the paper mentions that for the specific case where D2, which means we're looking at functions in the familiar two-dimensional plane, the concept of uniqueness sets is rather easily answered. How is that possible if the higher dimensional cases are so difficult? What's the trick here?
This is where it gets truly fascinating, and it showcases a beautiful interdisciplinary connection within mathematics. In the two-dimensional plane, which we frequently represent using complex numbers where any point, x, y, can be written as z equals x plus I.
Right, I being the square root of -1.
Correct. We gain access to an incredibly powerful set of tools, complex analytic functions, often called holomorphic functions. The paper provides a very elegant and clear example of this.
Okay, how's that work?
For any finite collection of distinct points in the complex plane, let's say E, Pj, and J1, where J just counts from 1 to n, the total number of points.
So just a bunch of points like P1,
Yes.
P2, P3.
Exactly. They can construct a polynomial Pe, defined as the product, Pez. Here, that capital A symbol, like sigma for sum, means we're multiplying together all the terms zpj for each point pj in our set E.
So for D2, if we have points P1, P2, P3, Pe would be ZP1, ZP3.
Perfect. That polynomial Pe is holomorphic. It's smooth in the complex sense. It's definitely not 0 everywhere, unless n0, trivially.
Yeah.
And by its very construction, it vanishes precisely at the points in the set E and nowhere else.
Okay, so we have a complex polynomial that's 0 at our points.
Yeah.
How does that connect back to our harmonic functions, which deal with real numbers and Laplacians?
That's the elegant step. It's a fundamental and well-known property in complex analysis that the real part of any holomorphic function is always a harmonic function.
Oh,
Always.
wow.
Yes. So if we take our Pe, which is by its very construction a holomorphic polynomial, and extract its real part denoted as Pe, then Pe becomes precisely the kind of function we're looking for. A non-zero harmonic function that vanishes exactly on that finite set of points E.
So yes, just take the real part. If Pe comes out as, say, A plus I, then
Yeah.
Epe is just A.
Exactly that. The notations you see means E is a complex number, x
Right.
plus I, and E is the operator that simply takes the real part, x. This clear and relatively straightforward construction in 2D, leveraging the structure of complex numbers, is precisely why the paper states that the D2 case is rather easily answered. It immediately highlights a profound difference in the analytical tools available for the two-dimensional realm compared to higher dimensions.
Okay, that makes sense. A nice trick using complex numbers. Now, we arrive at the central historical problem that this paper decisively resolves, a challenge that has mystified mathematicians for decades. The Scottish book Problem 151. This specific problem was famously posed by Arwave way back in 1936. What was the exact nature of this long-standing question, and what was the prize offered for its solution?
The prize, as charmingly noted in the actual Scottish book manuscript, which was this legendary notebook kept by mathematicians at the University of Lwów in Poland, where they jot down unsolved problems and offer prizes.
It's like a mathematical challenge board.
Exactly. The prize for problem 151 was a fondue in Geneva.
A fondue. I love it. So what was the $1 million or fondue dollar question?
The question itself was very specific. Does there exist a harmonic function defined in a region which contains a cube in its interior, which vanishes on all the edges of the cube? One does not consider f equals 0.
Okay, so harmonic contains a cube, vanishes on the edges of the cube, and isn't just the zero function itself.
Precisely. This is a profoundly important question, Precisely because, as we just discussed, if a harmonic function vanishes on too large a set, like an open set or a closed rectifiable curve, the maximum principle dictates that the function must be identically zero everywhere.
Right.
However, the edges of a cube are very specific one-dimensional line segments. It wasn't at all obvious whether a non-zero harmonic function could exist that would vanish exactly on these edges without being forced to be zero throughout the entire region. This uncertainty, this knife edge between trivial and non-trivial vanishing, is what made it such a persistent problem for, well, nearly 90 years.
And this paper, written by Ioann Vasilyev, provides a definitive positive solution to this exact problem. That remarkable finding is laid out as Theorem 1.
Indeed, it does, a positive solution. Theorem 1 states, for any natural number DO3, there exists a non-zero harmonic function on the whole spacetard, which vanishes on the de Vos skeleton of the unit cube Q.
Okay, lots to unpack there. DO3, so 3 dimensions or more. Non-zero harmonic function on the whole space, RD, vanishes on the DT skeleton of the unit cube QD. Let's make sure we rigorously define that crucial term, the DT skeleton. What exactly does that mean in the context of a d-dimensional cube?
That term is absolutely essential for understanding the scope and elegance of the theorem. The paper defines SKAD as the K-skeleton of the unit cube QD. The unit cube Q is simply the set of points where each coordinate a D is between -12 and 12. So QD is between elemental 12 cube.
Got it. The standard cube centered at the origin.
Exactly. When they refer to the K-skeleton, SKAD, they mean the union of all the K-dimensional faces of that unit cube.
Faces, like squares on a 3D cube.
Yes, but it generalizes. To be even more precise, the paper states it's the set of points on the cube's boundary cube that have at least deca of their coordinates fixed at either D12 or 12.
Okay, at least deca coordinates fixed at the boundary values. Let's try an example. For the theorem, we need the DD2 skeleton, so KDD2. That means points with at least DD2 coordinates fixed.
Right, which simplifies to DD plus 2, so at least 2 coordinates fixed at 12.
Okay, so points on the boundary where at least 2 coordinates are pinned to the surface.
Let's clarify this with concrete examples, as this is key.
Ollie.
For D3, which is our familiar 3-dimensional cube, the D2 skeleton refers to the 3-2-1 skeleton, S13. This is the union of all one-dimensional faces. And what are the one-dimensional faces of a 3D cube?
The edges.
Exactly, the edges. So for D3, Theorem 1 directly provides a positive answer to Wave's original problem about a non-zero harmonic function vanishing on the edges of a 3D cube.
Okay, that clicks perfectly. What about higher dimensions, say D4?
Right, consider D4, a 4-dimensional hypercube. In this case, the D2 skeleton would be the 4-2-2 skeleton, SO24. This refers to the union of the 2-dimensional faces. They're the square faces of a 4D hypercube. A 4D hypercube has 3D cells as its boundary, and the boundaries of those cells are these 2D square faces. So the theorem actually generalizes Wave's initial question, showing that this phenomenon extends beyond just 3D edges. It works for the 2D faces of a 4D cube, the 3D faces of a 5D cube, and so on. This precise definition clarifies the exact geometry where the function vanishes.
Fascinating. The paper also makes a very interesting side note. Theorem 1 is just false for the case where D2. Why is that? Especially after we just talked about how easily problems are solved in 2D using complex numbers. That seems counterintuitive.
It does seem odd at first glance, but this is a subtle but very important distinction. And it again circles back to the maximum principle we discussed earlier.
Okay.
For D2, the D2 skeleton becomes the 2-2 skeleton. What are the 0-dimensional faces of a 2D cube, which is just a square?
The corners,
Yeah.
the vertices.
Exactly, the vertices. Now, if a harmonic function vanishes only on the vertices of a square, it does not necessarily imply that the function is identically zero everywhere. We even saw an example of this construction earlier with our function for a finite set of points. In the plane, the vertices are just 4 points.
Right, we can make a harmonic function 0 at just those 4 corners.
Yes. However, Wave's original question for D3 was about vanishing on the edges. What corresponds to the edges in the D2 case?
Well, the edges of a square are its boundary.
Precisely. The one skeleton, S1, which would be analogous to the 3D edges, constitutes the entire boundary of the square. And if a non-zero harmonic function were to vanish on its entire boundary, the maximum principle for harmonic functions strictly dictates that it must be identically zero everywhere within that domain.
Ah, because its maximum and minimum must be on the boundary, and if the boundary value is 0 everywhere, the max and min are both 0, so the function must be 0 inside too.
Exactly. You cannot have a non-zero harmonic function that is 0 on all boundaries of a bounded region. So while you can construct a non-zero harmonic function that vanishes on just the vertices, the zero skeleton of a square, you absolutely cannot have one that vanishes on all its edges, the one skeleton of its entire boundary, without being the trivial zero function. This crucial difference between the d-dation 2 skeleton, vertices for D2, and the analog of edges, the boundary for D2, is why theorem 1 doesn't hold for D2.
That distinction really clarifies it.
Yeah.
Vanishing on the D2 skeleton is key, and for D2 that just means vertices, which isn't restrictive enough, whereas the equivalent of edges for D2 is too restrictive.
You've got it. It's a subtle point about the geometry involved.
The paper also mentions nodal sets
Did.
as a very interesting and classical topic closely related to this work. What exactly are nodal sets?
Nodal sets are quite simply the zero sets of functions. In other words, they are the specific collection of all points where a given function takes on the value 0, zf, sf, x, 0.
So the set the paper is constructing the function to vanish on, the D2 skeleton, is the nodal set of their function f.
Exactly. The study of where functions vanish their nodal sets is an astonishingly rich, complex, and long-standing area of mathematics. Its history dates back at least to the latter half of the 19th century, with foundational work by figures like James Clerk Maxwell.
Maxwell of electromagnetism.
The very same. He was deeply interested in spherical harmonics and their zero sets. This field is so deep that it's even connected to the still open Maxwell conjecture, which deals with the topology of level sets of harmonic functions, an ongoing area of research.
Oh.
So this connection underscores that the problem of a harmonic function vanishing on cube edges, while specific, is not an isolated curiosity. Instead, it's a modern contribution to a much larger continuous inquiry into the fundamental properties and behaviors of functions, particularly where they become zero. It's an active and central area of analysis.
So with the historical context set and our foundational definitions firmly in place, we arrive at the heart of Vasilyev's paper. The actual construction of this elusive non-zero harmonic function f dx that manages to vanish precisely on the D3 cube's D2 skeleton. The paper immediately introduces a very specific formula for this function. How do they build it?
Indeed. They construct an incredibly elegant function, f dt f dx, defined for any point x oki1 when 1xd in d-dimensional space are by the formula f dx1 oki x a up c is product again. 1 over yd means we take all pairs of indices I and j from 1 to d, where I is strictly less than j. And for each pair, we calculate by I2 sj2 and multiply them all together.
Perfect summary. Let's illustrate with DT3 again, just to be concrete.
Head idea.
If D3s are standard 3D space, the unique pairs where ij would be 1, 3, 1, 3, and 2, 3.
Right.
So the function f3 by 1 by 2 by 3 would be explicitly written out as the product of these three terms. f3 by 1 by 2 by 3 by 12 by 22 by 12 by 32 by 22 by 32.
Simple enough to write down, but clearly gets complicated fast as d increases. Oh, absolutely. The number of pairs grows quadratically with d.
The paper also makes an interesting observation, remarking that these FD functions resemble the Vandermonde polynomials. What exactly is a Vandermonde polynomial, and how is FD related to it? It sounds like they're leveraging something well known.
They absolutely are leveraging a deep and well-understood structure. A standard Vandermonde polynomial is a classic construct in mathematics, typically defined for a set of variables y1, y is vy1 iuig.
Ah, so it's the product of the differences, but without the squares.
Exactly. You're just multiplying the differences of all unique pairs of variables, uij. Now, if you compare this to our f dx function, f dx, apdigs, djij, you'll see the clever substitution they've made.
It looks like f dx is just the Vandermonde polynomial v evaluated by 12 by 22 8ix dt.
Precisely. f dx is exactly v by 12 by 22 ix dt2. This transformation, substituting y with by I2, is a stroke of genius because it allows them to import powerful known properties of Vandermonde polynomials into the context of harmonic functions, as we'll see in the proof.
Okay, that connection seems important. But first, how does this specific construction of f dx guarantee that it vanishes on the D2 skeleton of the unit cube? This vanishing property is the core requirement for solving Wave's problem.
This is the immediate and most crucial check, and it's quite elegant in its simplicity once you see it. Recall that a point x by one waves xd is on the D2 skeleton of the unit cube Q'd if it's on the boundary and has at least 2 coordinates fixed at 12.
Right.
So let's say a point x is on the D2 skeleton. This means there must exist at least one pair of distinct indices, say k and l, where 2k, l, and d, such that both xk and xl are fixed boundary values, i.e. xk, lf12 and xl equals x12.
Okay, so for a 3D cube edge, say where I1 12 and B2 12, and by 3 varies between xl 12 and 12, here K1 L2.
Perfect example. Now consider the term xk2 PBL2 that appears in the product defining FDX. If xk2 is 14, its L2 equals 42, xk2 and L2 equals 14.
Exactly, so xk2 pi L2 is also 14, and all of 2, 14 equals 7. Huh. So if a point is on the D2 skeleton, there's always at least one pair, KL, where both coordinates are 2, 12.
Yes, that's inherent in the definition of the D2 skeleton, points with at least 2 coordinates fixed at the boundary.
Okay, so for any point X on that skeleton, we can find a K and L such that xk2 by L2 equals 0.
Correct. And since this specific term, xk2 pi L2, is one of the factors in the overall product that defines FDX, remember, FDS is a product of all such by I2, ij2 terms.
Right.
If just one of these factors is 0, the entire product FDX must also evaluate to 0 at that point X.
Which is anything times 0 is 0.
Precisely. This is the critical, almost self-evident insight that ensures the function vanishes precisely where it needs to on the D2 skeleton. It is beautifully engineered into the function's definition.
That's very neat. The paper also briefly mentions 2 other functions, gx and hx. Are these essential to the main argument or just interesting side notes?
They are more in the realm of interesting variants that provide additional context and open up further questions. The first one is gx by r2 by it coest by I2 by j2.
So it's just FDX multiplied by all the coordinates by 1 through xt.
Yes. The paper notes that this gx is also harmonic, though they don't prove it there, and also vanishes on the D2 skeleton. For the same reason FD does, plus the fact that at least 2 coordinates are ekna 12, never 0, on the skeleton itself, so the extra by 1.xt factor doesn't mess that up.
So what's the point of mentioning gx?
Its inclusion tells us that the solution found by Vasilyev, FDX, is not unique. There can be multiple non-zero harmonic functions that vanish on the cube's skeleton. The paper actually poses it as an interesting open question for future research to describe all such functions.
Okay, so FD is one example, G is another. What about xgex?
The other function mentioned is xgex, xx1 at each, xdd a1 x each. Notice the differences, exponential factors instead of a1.xd and ixj instead of y2 by j2.
So it uses the actual Vandermonde polynomial Vx.
Yes, essentially. This hx is presented as a Laplace eigenfunction because it satisfies the property OEx or ADX.
The Laplace eigenfunction. What does that mean again?
It means that when the Laplacian operator A acts upon the function hx, the result is simply a scalar multiple of the original function hx. In this case, the scalar multiple is d, the dimension of the space.
So applying the Laplacian just scales the function by d.
Exactly. This highlights a different kind of fundamental property for a related function, demonstrating the rich variety of functions that can be constructed and studied in this area. They are not central to the main proof of Theorem 1 for HDD, but rather demonstrate the broader implications and connections within this mathematical landscape.
Okay, understood. Side examples showing related ideas. So while the construction of FDX makes its vanishing on the skeleton clear, the main technical hurdle, as the paper calls it, is rigorously proving that FDX is actually harmonic. The paper states that the proof of Theorem 1 boils down to that of Lemma 1. What exactly is Lemma 1 and why is it so central?
Lemma 1 is indeed the true mathematical heart of the paper's rigor, and its proof is what elevates the construction from a clever observation to a fully validated solution. Lemma 1 states very simply, let FD be as above and let DU too be a natural number. We have FDX equals 0 for all x elder 8.
So it just claims the function FD we just defined is harmonic everywhere.
Precisely. In plain language, this lemma asserts that the specific function FD, which we know vanishes on the cube skeleton by construction, is in fact a harmonic function across the entire d-dimensional space. The paper explicitly notes that once FD is rigorously proven to be harmonic via lemma 1, and given that we've already shown it vanishes on the D2 skeleton, the proof of the main Theorem 1 is complete.
So proving Lemma 1 is proving the core of Theorem 1.
Essentially, yes. The paper outlines 2 different proofs for Lemma 1. We'll focus on the first one presented in the text, which they actually label as the second proof methodologically, but present first, as it's arguably more direct and computationally illustrative, really showing the mechanism.
All right, this is where we need to delve into the intricate mathematical details. How exactly do they prove that f dx equals 0? Let's trace their steps precisely, ensuring we understand the mathematical reasoning and every part of this derivation, step by step.
Okay, let's meticulously trace their computational approach for the proof of lemma 1.
Introduce the Vandermonde polynomial vice and the substitution.
The proof begins, as we anticipated, by utilizing the standard Vandermonde polynomial. Define Vy, FDyi for a vector y, y1, xda in d-dimensional space.
Okay, Vy is the product of Uy.
Right. The crucial first step is to formalize the relationship we spotted. Our function f dx can be written as v by 12 by 22 s d2.
So f dx Vy where u as b a2.
Exactly. This substitution, letting ua as the I2 for each I from 1 to d, is fundamental. It allows us to connect the property we want to prove about fd, its harmonicity fd lies 0, to known properties of the Vandermonde polynomial v.
Utilize a known identity from prior research.
The second step is absolutely crucial, as it provides the mathematical backbone for the entire proof. The paper cites lemma 3.1 from a specific reference 15, which states a powerful and somewhat complicated identity involving the Vandermonde polynomial Vy. This identity holds true for any arbitrary real constants a, b, and c, and for all y and r, a, I, yi2 plus I plus b, he plus a, ye, I1, c, Vy equals 0.
Whoa, okay, that looks tense. Sum over I of yn2 plus I plus b times the second partial derivative of v with respect to ye plus sum over I at c times the first partial derivative of v, and all that equals 0 for any a, b, c.
Yes, it's a known general identity for the Vandermonde polynomial v. The beauty of this proof lies in choosing the right constants a, b, c to make this monster simplify.
Make a specific and clever choice of constants.
They make a very specific and insightful choice for the constants a, b, c in this general identity from step 2. They choose a0, b0, and c12.
Okay, a0, b0, c12. Let's see what that does to the identity.
If a0 and b0, then the term yi2 plus I plus b just becomes ui2, much simpler. And the coefficient c in the second summation becomes 12. So substituting these choices into the general identity gives us the much simpler equation. EECEY IOI2 plus 12s. AE equals E equals 0.
Okay, that's definitely better.
To eliminate the fraction and work with integer coefficients, they just multiply the entire equation by 2. This gives us the refined target identity that they will use. 2ei1 ii2 vv plus i1e plus he i1 euro is 0.
Got it. So 2p of a plus some v, where v is partial root e and v is the second partial.
Exactly. This simplified identity, derived from a known general one by a smart choice of constants, is what we will now directly connect to the Laplacian of f dx. This is the crucial pre-computed result they leverage.
The crucial chain rule derivation relating e of dx to vx.
Now for the calculus, this is the most detailed part where we compute the Laplacian of f dx by meticulously applying the chain rule, because fdd depends on x through the EAT substitution. Our goal is to compute f dx I11 ogo AAA2 F2 ATAPX.
Which is AEEA2 where she AKAD where E2 APX.
Which is II1 arrow AAI AAE where ye. Correct. So each ye is a function of only the corresponding 11. First, let's compute the first partial derivative of f dx, focal vy1, re-v, with respect to a single 11. We use the chain rule. If u, vy1 lead and v euro.
Okay, derivative of v with respect to ye times the derivative u with respect to e out.
Right. And since ye is IR2, its derivative with respect to e is simply irio 2 to a u.
Got it.
So the first partial derivative is irio do to e to b. Next, we need the second partial derivative with respect to the same irio, so irio to v. This means taking the derivative of the expression we just found, 2 e with respect to ev again, 2 in ee.
Okay, now we have a product of two things that depend on illa, 2AV and EU, since ye depends on LA. So we need the product rule.
Exactly. Let u irio and v ye. The product rule is EE plus EE.
Okay. Derivative of u irio e is just 2. So the first term is 2e e2 euro e.
Ugh.
Now for the second term, ye, we need to figure out that derivative here. Eo. Chain rule again. Because ye depends on z through ye.
Precisely. So E becomes yuri.
Which is every be ye.
Correct. And we already know yuri to yuri.
So iri simplifies to ye.
Yes. Now substitute this back into the second term of our product rule. E becomes to iri, to ear.
Which multiplies out to 4 by I2.
Perfect. Now combining the two parts from the product rule, the 2 uri, and this new term, the full second partial derivative for a single coordinate c is 2 Erie VE plus 4 by AE plus 4 by AE.
Summing for the Laplacian and connecting to the simplified identity.
Now we have the second partial derivative with respect to each CA. To get the Laplacian or x, we just sum these up over all A from 1 to D, or 1 to EA, AA E2, EA plus 4 by IE, EAT.
Okay, sum of those two terms for each A.
We can split the sum and rearrange the terms.
Okay.
AAE UREA plus IE1 4 by IE plus AA1 4I2 EA ERA plus 4A AMEA2 EA plus AE2 ERA A2 plus 4A I1 by A2.
Looks good.
Next, let's factor out a 2 from the entire expression for FDX, FDAIAX plus 2AIL1 by I2 plus 2AI1 by I2. And here is the elegant conclusion. Take a close look at the expression inside the square brackets. FVA plus 2AII1 by I2.
Okay, I'm looking. Sum of first partials plus twice the sum of by 2 times second partials.
Now compare that to the simplified lemma 3.1 identity we derived earlier in step 3. Remember that one?
This 2KIAU plus FEUE equals 0, 0.
Exactly. Look again at what's inside our brackets. Plus 2u by 2. It's exactly the expression from step 3, but with ye replaced by die 2.
Whoa, it is.
And since that identity from lemma 3.1 evaluated with ye, fa2, is known to be identically equal to 0.
And the entire expression inside our brackets must be 0.
So therefore, FGX plus 0, 0, 0, 0.
QED.
QED. This rigorously proves that FDX is indeed a harmonic function for all x and r.
That is truly remarkable. The way they connect a known, fairly complex identity for van der Waals polynomials with this very clever change of variables substituting by on 2 for yi. And painstakingly, but beautifully, apply the chain rule and product rule to show that the Laplacian calculation mirrors that identity perfectly. It's a beautiful demonstration of mathematical ingenuity and how deep properties can unlock seemingly intractable problems. It's not just a clever trick. It's almost like finding a hidden blueprint within a well-understood structure and using it to build the solution. Incredible. So having provided a definitive solution to the Scottish book problem using FDX, the paper doesn't just rest there. That would be impressive enough. But it immediately moves into a more ambitious realm, constructing new families of harmonic polynomials that share a common zero set, this time within a unit ball in Rn for dimensions in 4. How do they manage to generate these entirely new families of functions? It sounds like a big leap.
It is a significant step, and they achieve this by employing a very powerful and perhaps more abstract yet incredibly effective concept known as harmonic morphisms.
Harmonic morphisms. Okay, new term. What's the intuition?
To give you an intuitive grasp, think of a harmonic morphism as a special type of mathematical mapping or transformation between different spaces. Let's say you have a map, sci-fi, that takes points from an n-dimensional space Rm to an n-dimensional space Rn. We write this as Rm Rn.
Okay, a map from one space to another.
This map is a harmonic morphism if it possesses a unique property. Whenever you have a harmonic function, let's call it h in the target space, Rn, so Ret equals 0 in Rn, and you compose it with this mapping, meaning you first apply to your input x in Rm to get a point of x in Rn, and then you apply the harmonic function h to that result, giving x, resulting function h, Rh composed with phi, which is now a function defined on the source space Rm, will also be harmonic. So Rnm equals a 0 in R.
Wow. So it's like a machine that takes harmonic functions from the target space and pulls them back to create harmonic functions in the source space.
Exactly. It's essentially a harmonicity-preserving transformer. If you start with something harmonic in Rn and pull it back through, it stays harmonic in Rm. This property is extraordinarily useful because it provides mathematicians with a systematic and rigorous method to generate new harmonic functions from existing ones. If you can find such a foe, you've essentially found a factory for new harmonic functions.
That sounds incredibly powerful.
It is. And the paper then formalizes this power through Proposition 1.
Okay, let's look at Proposition 1. The paper seems to lay out 3 key results for effectively using these harmonic morphisms. Could you meticulously break down those 3 points for us?
Absolutely. Let's unpack Proposition 1 as it's the theoretical engine driving the construction of these new families. Suppose we begin with an initial collection or family of harmonic functions. Let's call them Fj10. This is an infinite sequence of functions, f1, f2, f3. This family is assumed to be linearly independent, which means that no function within this collection can be expressed as a finite linear combination of the others. They are fundamentally distinct, none is redundant.
Right, like basis vectors.
Good analogy. Each fj is also a harmonic function in Rn. The paper specifies NO3 here. And crucially, they all share the exact same zero set within a small ball, B0 day, centered at the origin. So ZF1 equals ZF2 inside this little ball.
Okay, infinite family, linearly independent, harmonic, same zeros locally. Got it.
Now, if we take a non-constant harmonic morphism, Rn, meaning isn't just mapping everything to a single point, it's actually transforming the space in a meaningful way, then three significant consequences emerge. Point one, Sj. Fj is harmonic in R for all Jn.
Okay, Sj is the new function Fj. And this is just the definition of the harmonic morphism, right? Pulling back Fj through preserves harmonicity.
Exactly. This is the most direct consequence and is essentially the definition of a harmonic morphism in action. It explicitly confirms that applying the morphism to any of our initial harmonic functions fj preserves its harmonicity. The V symbol, just to remind everyone, denotes function composition, so fjx means fjx. Point two, the new family, Shj, which is fjj, remains a linearly independent family in ARM.
Ah, so the transformation doesn't accidentally make some of them combinations of others. They stay distinct.
Correct. This is a very important point for generating new and distinct functions. It follows because a non-constant harmonic morphism has a property related to being open or surjective onto its image, which intuitively means it maps ARM onto a reasonably large part of Rn. It doesn't collapse the space too much. Therefore, it doesn't collapse distinct input functions fj into identical or dependent outputs hj. If our initial set fj were linearly independent, they remain distinct and independent even after undergoing the transformation by aj. Point three, there exists some possibly smaller positive radius 0, 1, such that the zero sets of all the new functions are also identical within this smaller ball. 0, 1, 0, 1 for all aj.
So the new family aj also shares the same zero set, at least locally near the origin.
Yes, exactly. This point confirms that the newly generated family functions inherits the property of sharing the same zero set, at least locally within some potentially smaller ball B01 around the origin. This is critical for the paper's goal of generating new harmonic functions that exhibit the desired vanishing properties on a specific set.
Okay, so putting it all together, if you have one family of independent harmonic functions vanishing on a set, and you have a harmonic morphism, you can use it to generate another infinite family of independent harmonic functions that also vanish on basically the same set locally.
You've got it. Collectively, these 3 points demonstrate the profound power of harmonic morphisms. They provide a rigorous mathematical framework that allows mathematicians to generate an entire lineage or family of new harmonic functions that inherit and maintain important properties, harmonicity, linear independence, and common zero sets from an initial set of functions. It's a powerful engine for discovery in this area.
This all sounds quite abstract, though. Can the paper provide concrete, explicit examples of these harmonic morphisms and the resultant polynomials they generate? That would really help ground this powerful concept in something tangible.
This is precisely where the paper shines, moving from the abstract theory outlined in Proposition 1 to very specific constructive examples. They differentiate between cases for even and odd dimensions for the source space, R.
Even dimensions Rm, where M2n for N01.
Here, the source space Rm is R2n. They default specific mapping. Ascent 1 of Run, R2n, R2. This map takes a point x from two-dimensional space and maps it to a point 1x topipex in the two-dimensional plane R2.
Okay, mapping from R2 into R2, what are 1 and 2?
Let's define its components meticulously. The first component, 1x, is defined as a sum of differences of squares of paired coordinates. 1x s by 12 by 22 plus by 32 by 42 plus plus by 2 and f1 u by 2.
So it pairs them up by 1 by 2 by 3 by 4, etc., and takes Zod 2 to 2 for each pair, then adds those up.
Exactly. For instance, if n1, so m2, 1x is simply by 12 by 22. If m2, so m4 is by 12 by 22 plus by 32 by 42. The second component, 2x, is defined as a sum of products of paired coordinates. E are multiplied by 2. 2 by 1 by 2 plus 2 by 3 by 4 plus 2 by 2 and 1 by 2.
Okay, similar pairing. Two sides even for each pair, then sum them up. So for n1, m2, it's 2 by 1 by 2. For n2, m4, it's 2 by 1 by 2 plus 2 by 3 by 4.
Perfect. Now, the paper, by referencing another source 21, states that this specific mapping, 1R2, is indeed a known harmonic morphism from R2n to R2. This isn't something they reprove here, but rather a known established result they are utilizing.
So this specific is our harmonicity-preserving transformer from R2n to R2.
Hmm.
And what kind of polynomial is 1x itself? The paper uses several specific terms to describe it.
Yes, the paper provides a very precise characterization of 1x itself, calling it an irreducible, non-degenerate, quadratic homogeneous harmonic polynomial. Let's break down each of these terms for a full understanding.
Okay.
Irreducible. In the context of polynomials over real numbers, an irreducible polynomial is one that cannot be factored into two non-constant polynomials with real coefficients. It's essentially as simple or fundamental as it can get in terms of factorization. By 12 by 22 can be factored as by 1 by 2, by 1 plus by 2, but maybe for n1 it becomes irreducible. We should probably just take their word for it being irreducible for the general n.
Okay, can't be factored further.
Non-degenerate. This means the polynomial truly depends on all 2n variables in R2n. You cannot simplify it by, for example, making a change of coordinates that would reduce the effective number of variables it genuinely involves. It's not a trivial case where some variables could be ignored.
Makes sense. It uses all by 1 through by 2n.
Quadratic. This indicates that every single term in the polynomial has a total degree of 2. For instance, by 2 is a quadratic term, and there are no terms like a z degree 1 or by I3 degree 3.
Right. All x something 2.
Homogeneous. This means all terms in the polynomial have the same total degree. Since all terms in 1x are of degree 2, like by 12, by 22, etc., it is homogeneous of degree 2.
Okay. And harmonic. Is 1x itself harmonic?
Yes, that's the last part. 1x
Right.
is itself a harmonic polynomial. We can check this. The second partial derivative of by 2k1, 2, 1 by 2k1 is 2. The second partial of minus up 2k2 minus by 2 is minus 2. All other second partials are 0. So the Laplacian one is the sum of 2 plus minus plus 2 plus minus 2 plus man, which sums to 0. So yes, 1 is harmonic.
Neat. So the first component of the harmonic morphism is itself harmonic.
Indeed. Now, the truly crucial part, which extends results from earlier work referenced as 16, is that this 1x divides infinitely many linearly independent harmonic polynomials. This is the generative power in action.
How do they get the infinite family?
The example they give for such a family is derived by looking at the complex combination 1x plus I2s.
Combining the two components into a complex number, like ZA's x plus IOE.
Exactly. Let x 1x plus IO2x. This turns out to be a holomorphic function related to sums of by k1 plus I by 2k2. Then they consider powers of this function, specifically x2k1x plus I2x2k, for any natural number k1, 2, 3.
Raising the complex function to an even power.
Yes. Since x is holomorphic, any power x to k is also holomorphic. And we know the real and imaginary parts of holomorphic functions are harmonic. So they state that the imaginary part of this expression x to k, which is x plus I2x2k, gives an infinite family of harmonic polynomials, one for each k.
And these are linearly independent.
Yes, they state these are linearly independent, building on the result from 16, and crucially, they will share the same zero set locally, inherited from the properties shown in Proposition 1. This demonstrates how the single harmonic morphism acts as a powerful engine for constructing vast new families of these unique harmonic polynomials in even dimensions m to n.
Odd dimensions are, where m2k plus 1 for ko2, but restricted to mu5 for non-trivial examples.
Okay, that covers the even dimensions. What about odd dimensions, Om?
This case is presented more abstractly, relying on a result from another source 4, specifically example 5.2.7. They define a map, a Mickey AR2XC. This map looks somewhat similar in spirit, but is more general. x2x is defined via a complex expression, m2xj.
Whoa, okay, x by 1x. X is the point, What's z and the xj?
Wait. Here, z is a complex number formed from the last two coordinates of xz equals xm1 plus xm. And the xz terms are complex-valued coefficient functions that depend only on this complex variable z. The sum runs from j1 to m2, multiplying each xjz by the corresponding coordinate xj. The result is a complex number, whose real part is 1 and imaginary part is x2.
That's quite intricate. So the mapping depends on coefficients xj, which themselves depend on the last two coordinates combined into z.
Yes. Now, the crucial condition for this specific map to be a harmonic morphism from arm to c, the complex numbers, which is equivalent to R2, is that the sum of the squares of these coefficient functions must be identically 0. The sum of the squares of the coefficients has to be 0. How can that happen if they are functions?
It has to hold for all z. This is a very specific algebraic constraint that the xjz coefficient functions must satisfy. They are complex valued functions, so xg2 is also complex. The sum must be the complex number 0.
Okay, that seems like a tough condition to meet. How do they satisfy it?
To satisfy this stringent condition, they employ a mathematical ansatz,
which is essentially an educated guess or a proposed form for a solution that is then verified, taken from reference 4, specifically section 6.8.6. This ansatz gives a specific complex vector form for ANT1 and ANTC2. They suggest using ANSTAT, 1G2, I1 plus G2 NASCD, but this specific form only works if M23, meaning M5. Let's reread that part. It says ANSTTE can be chosen using an ansatz. Example 6.8.6 and 4 gives a way to construct vector functions ANSTTS such that the sum of squares is 0, provided M2 or 3, which means M5. The paper doesn't write out the general form of ANS from that example, but asserts that such choices exist.
Okay, so they reference a method from 4 that guarantees they can find coefficient functions such that an ANSTT2 will invest 2 provided the dimension M is 5 or greater.
Exactly. Once this condition is met, the map, Ceph1, 2, 2, 2, defined using these Ashke, is a harmonic morphism from ARM to R2, from MO5. Then, just like in the even-dimensional case, one can take known harmonic functions E2, like the real or imaginary parts of stick, and pull them back using Ashke to get new harmonic functions in WARM, generating new families.
And why the restriction, MAF5?
The paper makes an important note regarding this dimensional restriction. The general theory might apply for MAL3, but for MO3, a standard 3D space, this specific construction apparently does not yield any non-trivial examples, meaning it doesn't give anything new or interesting that couldn't be done by simpler means. And for MO4, a 4D space, that dimension was already covered by the more direct construction using in the even-dimensional case we just discussed. Therefore, the truly new insights and the generation of novel families of harmonic polynomials from this odd-dimensional construction are specifically applicable for Math 5.
Okay, so the machinery works, but only gives genuinely new stuff for dimension 5 and up in the odd case.
That seems to be the conclusion presented here. It demonstrates how mathematicians meticulously explore the boundaries and applicability of their results.
This really illustrates the incredible power and scope of the deep theory of harmonic morphisms. It's not simply about solving one specific problem like the Scottish Book 1, but about providing a robust theoretical framework that can be used to construct entire families of these unique harmonic polynomials with shared properties. It truly highlights the generative and expansive nature of advanced mathematical concepts. Now, in the paper's appendix, the authors circle back to an open question they touched upon earlier in the introduction. Given a finite union U of affine lines in ARD, under which condition on U does there exist a non-zero harmonic function f such that fu equals 0, 0? This seems to be a much more general formulation of the problem we discussed earlier with the cube edges, which are just a specific union of lines.
This question is indeed surprisingly complex, even when you restrict your focus just to the two-dimensional plane, D2. The complexity is significantly simplified in D2, however, thanks to that powerful analytical tool we mentioned briefly before, the Schwartz reflection principle for harmonic functions. In many scenarios involving lines, this principle effectively collapses multiple possibilities into straightforward conclusions.
Right, the Schwartz reflection principle. Could you provide us with an intuitive understanding of what it does, again, especially in the context of lines? It sounds like a pivotal tool here.
Certainly. Imagine you have a harmonic function defined on one side of a straight line in the plane, say the upper half plane, defined by y0. And, crucially, that this function is 0 on that boundary line, y to 0, 0. The Schwartz reflection principle fundamentally allows you to analytically extend that harmonic function to the other side of the line, the lower half plane, y is 0, by reflecting the function across that boundary line.
How does the reflection work?
If fxy is the function for y0 and fx0, 0, 0, the reflected function fxy for y0 is defined as fxy equal fxy. You flip the sign of y and negate the function value. This ensures the extended function is smooth and still harmonic across the line y0. This principle is a remarkably powerful tool for both constructing and understanding harmonic functions, particularly in geometric settings that involve planar boundaries like lines.
Okay, so you can extend harmonic functions across lines where they are 0. How does that help with the union of lines problem?
Well, the paper specifically states that if a union U of lines in the plane consists of 3 lines where 2 are parallel, and the third line intersects them, and if this third line is not orthogonal, meaning not at a perfect 90-degree right angle to the parallel lines.
So like 2 horizontal lines and a diagonal line crossing them.
Exactly. In that configuration, the paper states that any harmonic function vanishing on U, all 3 lines, must be identically 0. They say this arises from easy geometric observations, coupled with one more application of the Schwartz reflection principle. Essentially, if you reflect across the non-orthogonal line, you get another pair of parallel lines at a different angle. If you keep reflecting across these lines, the zero set becomes increasingly dense in the plane, eventually forcing the harmonic function to be zero everywhere.
Ah, the reflections sort of fill up the space with zeros.
That's the idea. This dramatically simplifies the problem in D2, as it eliminates most configurations of 3 lines, leaving only one specific non-trivial case where a non-zero harmonic function could potentially exist.
So if the intersecting line isn't at right angles to the parallel ones, the function has to be 0. What's the one non-trivial case that remains for D2 and you have 3 lines?
The only remaining non-trivial case discussed here is when the 3 lines form the boundary of what they call an orthogonal half-strip.
Orthogonal half-strip, okay.
Yeah. They rigorously define this half-strip H as the set of points, when 1 by 2, in R2, so it's the 0 A by 2, so it's in the upper half plane, including the x-axis, and point is 2 by 1 A2, so it's between 2 vertical lines.
Okay, so it's bounded below by the x-axis, x2, 0, from x1, 2 to by 1, 2. Bounded on the left by the line by 1, by 1, by 1, by 0, and by 2, and bounded on the right by x1, on 2, for by 2, 0, and it goes up infinitely in the by 2 direction.
Perfect visualization. The boundary of this region consists of 3 lines, or line segments, the segment on the x-axis and the 2 vertical half-lines. This is the very specific geometry where the question of a non-zero harmonic function vanishing on its boundary becomes interesting and non-trivial in D2.
This is truly intriguing. Can they actually construct a non-zero harmonic function that vanishes on the boundary of this very specific half-strip? That sounds incredibly challenging given the complexity and the infinite extent.
They absolutely do. They provide a remarkable, though quite complicated-looking formula for such a function, which they denote S0 by 1 by 1 by 2. Now, the formula itself is quite long and involves nested terms.
Yeah, I'm looking at it in the paper. It's a bit of an eyeful. Cos pace 1 sin by 2 times the square root divided by something involving sin by cosh by 2 plus the square root times another factor.
Phew. Exactly. While we won't try to read out every single term, let's understand its structure and the brilliance behind it. The function S0 by 1 by 2 is a sophisticated combination of trigonometric functions, cos make 1 and sin by 1, which handle the behavior in the I by 1 direction, and hyperbolic functions, sin S2 and cosh cos 2, which handle the behavior in the cos direction.
Hyperbolic sine and cosine. Remind me of those again.
Sure. Sin x es e by 2 and cosh x plus e by 2. Unlike periodic trigonometric functions, sin and cos, hyperbolic functions, sin and cosh, grow exponentially, except sin 0, 0, and cos 1. They're fundamental in solving Laplace's equation, which defines harmonic functions, in geometries involving strips or half-strips, precisely because their exponential behavior matches the potential decay or growth in the unbounded direction.
Okay, so trig for the bounded direction by 1, hyperbolic for the unbounded one by 2. Makes sense. The formula also involves square roots, power 12, and reciprocals, power name of 1.
Yes, it's quite algebraically complex. But let's see why this intricately designed function S0 by 1 by 2 vanishes precisely on the boundary of the half-strip H. This is where its engineering becomes apparent.
Okay, let's check the boundaries.
Boundary 1 by 1 by T2, the vertical boundaries. Look at the very beginning of the formula. It starts with cos by 1, sin by 2. Oh, what is cos by 1 when by 1 by 1 is on 82?
Cos 2 is 0, cos by 2 is also 0.
Exactly. Since cos by 1 is a direct factor right at the start of the entire product, if cos by 1 is 0, the whole function factorial becomes 0. This elegantly ensures vanishing on both vertical boundaries.
Neat. Okay, what about the bottom boundary?
Boundary 2 by 2 by equals 0. The horizontal boundary. Again, look at that first factor. Cos by 1, sin by 2. What is sin pi 2, 1 by 2, 0? By is 0, sin 0. E0, E0, 2 equals 1, 1, 2 equals 0. Correct. So sin 0 is 0. Because this sin 0, 2 term is also part of that initial factor, its 0 value forces the entire function S0 to be 0 all along the bottom horizontal line segment of the strip's boundary, where next to 2 by 1 mic 2 and die 2 equals 0.
Wow. So the function is explicitly built to have factors that become 0 on each part of the boundary.
Precisely. Now, the paper states that verifying S0 is harmonic, ideas checking S0, 0, 0, is a routine computation. Given the sheer complexity of the formula, that comment truly highlights the profound depth of knowledge and the significant computational effort that even routine checks demand in this field for expert mathematicians. It's definitely not trivial for us mortals.
No kidding. It's astounding that mathematicians can even discover such complex formulas for these specific geometric situations. It doesn't seem like something you could just stumble upon randomly. How do they find these things?
You're absolutely right. It's rarely a random discovery. The paper briefly explains the typical strategy. Such formulas are often found using powerful techniques like conformal mappings.
Conformal maps? What do they do?
These are special types of geometric transformations, usually in the complex plane, that possess the unique property of preserving angles locally. They can warp shapes, but tiny angles remain unchanged. Mathematicians use conformal mappings to transform a simpler geometric domain, for which they already know existing harmonic functions that vanish on its boundaries, like the upper half plane or maybe a full strip, onto the more complex target domain, like the specific orthogonal half strip we just discussed.
So they map the complicated shape to an easier one.
Or vice versa, map the easy shape onto the complicated one. Once the mapping function, say WGZ, is established, they can then take a known harmonic function HW that vanishes on the boundaries of the simpler shape in the W plane and compose it with the inverse map Z, ZG1W, to get a harmonic function HGZ in the original Z plane that vanishes on the transformed boundaries, which are the boundaries of our target shape.
Ah, so they combine known simple solutions with these angle-presuming maps.
Exactly. They might use known harmonic functions, like AMZ, which is y, or AMZ, which is 2 by psi, or maybe things involving exponentials, like S sin or sin x sin, which are harmonic and vanish on certain lines. By carefully composing these known building blocks with the appropriate conformal maps, they can derive these incredibly intricate but correct formulas, like Bessie, for harmonic functions that vanish on the boundaries of much more complex geometries. It's a brilliant example of how mathematicians build upon a vast arsenal of existing knowledge and sophisticated tools to solve new and challenging problems.
That makes a lot more sense than just guessing the formula. Okay, moving beyond lines and half strips in 2D, the appendix extends its analysis to consider prisms in three-dimensional space, R3. What's the setup here, and what were their findings regarding harmonic functions vanishing on the boundaries of these prisms?
Right. This is covered in Proposition 2, which deals with this 3D scenario.
Right.
They begin by rigorously defining the specific type of prism they are investigating.
Okay, what kind of prism?
They start with a coordinate plane, specifically WR3 by 1 equals 0. Which plane is that?
By 1, so 0, that's the by 2 by 3 plane.
Correct. Within this by 2 by 3 plane, they take a bounded triangle, which they denote P.
So just a standard triangle sitting in the by 2 by 3 plane.
Exactly. The corresponding two-sided unbounded prism CP is then formed by taking this triangle P and extending it infinitely in both directions along the by 1 axis, the axis perpendicular to the plane the triangle lies in. So CPX R3, XV plus 0, 1, where VPR.
Let's break down that notation. V is a point inside the triangle P in the by 2 by 3 plane. E1 is the unit vector in the by 1 direction, so 1000 R is any real number. So V plus E1 means you take a point in the triangle and shift it forwards or backwards along the by 1 axis by any amount too.
Perfect. So you're essentially taking the 2D triangle P and sweeping it out infinitely along the entire by 1 axis, creating an infinitely long prism with P as its cross-section.
Got it. Like an infinitely long Toblerone bar if P was a triangle.
Exactly like that. Now, the proposition presents two very distinct and important statements about harmonic functions vanishing on the boundary team P of this infinite prism. Statement 1, zero function. It asserts that if the base triangle P is not one of 4 very specific types of triangles.
Uh-oh, special cases coming up.
Yep. The special triangles are an equilateral triangle with angles 60 degrees, 60 degrees, 60 degrees, an isosceles triangle with angles 30 degrees, 120 degrees, a right triangle with angles 30 degrees, 60 degrees, 90 degrees, or a right isosceles triangle with angles 45 degrees, 90 degrees, if P is any other type of triangle.
Like a random scaling triangle.
Exactly. If P is not one of those 4 specific types, then any harmonic function that vanishes on the boundary of the prism CP, F equals 0, must be identically 0 everywhere.
Wow. So for most triangles, there's no non-trivial solution. Why?
Sure.
What's special about those 4?
The justification for this, as stated in the paper, relies on a result from another source 5. This result shows that for these non-special triangles, if you start reflecting the triangle P across its sides and then reflect the reflections across their sides and so on, these successive reflections are dense in R2.
Dense, meaning they eventually cover the entire by 2 by 3 plane.
Essentially, yes. They fill the plane so completely, overlapping chaotically, that if our harmonic function is 0 on the original prism boundary, which includes the sides derived from P, its reflections will force it to be 0 on this dense set of reflected prism boundaries. And if our harmonic function is 0 on a dense set, it has no choice but to be 0 everywhere in the entire 3D space. There's no room left for it to be non-zero. Statement 2, non-zero function. Conversely, if P is one of those 4 specific special types of triangles we just listed, equilateral 30, 30, 120, 30, 60, 90, or 45, 45, 90, then a non-zero harmonic function of S does exist that vanishes en route to CP.
Ah, so for these special triangles, a solution exists. Why are they different?
The proof for this relies on yet another source 10, and crucially, another application of the Schwartz reflection principle. For these special triangles, their successive reflections much like images in a perfectly designed kaleidoscope, form a tiling of the whole plane, R2, without any self-intersection or gaps.
Like bathroom tiles, they fit together perfectly.
Exactly. They perfectly tile the by 2 by 3 plane. This perfect non-overlapping tiling allows a harmonic function that vanishes on the boundary of the original prism CP to be extended harmonically to the entire 3D space by simply reflecting it across the prism's side faces, which correspond to the edges of P. Because the reflections tile perfectly and without overlap, the function remains well-behaved and harmonic across the entire space. And critically, because the zero set doesn't become pathologically dense, the function can remain non-zero somewhere, demonstrating its existence.
That is an absolutely fascinating distinction. It truly means that very specific geometric properties of the base triangle, whether its reflections tile the plane nicely or chaotically, fundamentally determine whether a non-zero harmonic function can even exist that vanishes on the boundaries of its corresponding infinite prism. It's a deep interplay between the geometry of the base and the analysis of the function.
It is indeed a beautiful connection. And the paper takes this even further by pointing out that for a closely related case specifically, where the base P is the unit square, a different analysis applies. A square's reflections also tile the plane perfectly.
Right, like a checkerboard. A square isn't one of the four special triangles, but it does tile, so should a non-zero function exist?
Yes, and in this case, mathematicians Loganov and Melnikova, references 16, actually provided an explicit formula for such a function. This function, x, ki psi of x, is defined in d dimensions, so for a hyperprism based on a d1-dimensional hypercube. But let's think d3 for a square base P in the 2 by 3 plane. The formula looks like a product of sine functions for the coordinates in the base, and a single hyperbolic sine function for the coordinate along the prism's axis by 1 in our setup. For a d-dimensional prism based on a d1 cube, it would be sinoid no 1 sin 1 2 by 2 sin ida 1x d na sin ida 1x 2 by 1 sin ida is otherwise sin ida is 1 is d 1 sin ida okay, the function would look like sin ida 1 is 2 by 3 and such 3 no 1 1 sin ida is 2 by 2 no 1 at 2 by 3. Okay, sin for the axis direction by 1, sin for the base directions by 2 by 3. That formula looks like a beautiful blend of periodic oscillations in the base and exponential growth decay along the axis. What's the specific condition for this function to be harmonic?
Yeah.
There would be some constraint on those as coefficients a1, a2, a3.
You're spot on. This function for x is harmonic only if the real numbers a1, a2, and ox satisfy a very specific critical mathematical condition relating their squares. Let's take the general d-dimensional formula. Sin endo su x add 1x d down of 1, sin and ed c. The condition for this to be harmonic is add 2 equals a12 plus a22 plus add those. The square of the coefficient for the sin term must equal the sum of the squares of all the coefficients for the sin terms.
Ah, like a Pythagorean theorem for the coefficients. So for our 3D example, it n by 1 by 2 by 3, a2 adosa sin, a do a2 sin, a2 by 2 sin, a do 2 3. The condition would be a12 e d to s a22 plus a32. Wait, that seems wrong. Let's reread the formula. Sin, n1 by 1. 2 sin add to us 1x1 in edo is okay, so the sin is on the last coordinate xt. The condition is added to 2 to 1 plus added through 12. So for our 3D prism along by 1, maybe the function should be add joke x added to sin a through 3 sin add through 1 and the condition is a12 is a22 plus a32.
Yes, that structure fits the description and the condition perfectly. If this precise condition a12, a32 plus a32 holds, then this specific crux is rigorously guaranteed to be a harmonic function.
And does it vanish on the boundary of the prism based on the square?
Yes, it's also quite clear from its construction. The boundary of the prism based on the unit square, say by 2 from -12 to 12, by 3 from -12 to 12, involves planes like by 2 equals 12 and by 3 equals to -12. If we choose the coefficients a2 and a3 correctly, for instance a2 and a3 equals whole, then sin a2 by 2 becomes sin x2, which is 0 when by 2 equals sin of 12, or any integer multiple. Similarly, sin x3 is 0 when by 3 equals other 12. So the function x, it's sin x2, sin a1 by 1, where a12 equals 2 plus 2, would vanish on the side faces of the prism corresponding to x2 and a 12 and x3 and a 12.
Perfect. So we have an explicit non-zero harmonic function vanishing on the boundary of the square-based prism, provided that Pythagorean-like condition on the coefficients holds.
Exactly. This demonstrates that even for different geometric shapes and configurations, like cubes versus prisms, similar mathematical structures and conditions can lead to explicit solutions. The paper leaves us pondering further questions on finding such explicit formulas for other complex shapes and comprehensively classifying these non-trivial functions. It's clear there's a deep connection between the geometry of the zero set and the possibility of constructing these functions. #outro.
So what does this all mean for us? We began this deep dive with a captivating prize problem from 1936, a nearly century-old mystery about functions vanishing on the edges of a cube. And we've journeyed deep into the elegant, sometimes exquisitely intricate mathematical machinery that Ioann Vasilyev used not only to solve it, but to extend its implications far beyond the original question.
It really was a fantastic journey through some beautiful math.
From defining the foundational concepts of harmonicity and the subtle nuances of uniqueness sets, to the ingenious application of van der Waals polynomial properties, and the meticulous step-by-step application of the chain rule in complex derivations, and finally, to the powerful generative capabilities of harmonic morphisms. This paper is a profound showcase of the beauty and rigor inherent in pure mathematics.
It really brings together different areas quite nicely.
It's a testament to how seemingly abstract mathematical concepts can have very concrete applications in resolving long-standing problems and pushing the absolute boundaries of our knowledge.
Absolutely. If we connect this to the bigger picture, this paper truly transcends the singular achievement of solving one historical problem. It provides entirely new tools like the explicit construction using van der Waals properties, or the reminder about harmonic morphisms, and perhaps even more importantly, it raises new and exciting questions that open up vast avenues for future research.
Like classifying all functions vanishing on the cube skeleton, or figuring out the conditions for unions of lines in higher dimensions.
Exactly. The work on constructing entirely new families of harmonic polynomials using morphisms, and the very detailed analysis in the appendix of how specific geometric zero sets behave, whether we're talking about orthogonal half strips or the nuanced conditions for prisms based on tiling triangles, really broadens the field for further exploration.
Yeah.
The sheer elegance involved in deriving FDX's harmonicity, the undeniable generative power of harmonic morphisms in creating novel functions, and the precise geometric and algebraic conditions required for a non-zero function to exist on a prism's boundary. These are all compelling testaments to the incredible depth and continued relevance of this field. This is how mathematics progresses, continuously building on prior work to create new insights, develop new methods, and unveil more of the universe's underlying mathematical order.
Here's where it gets truly thought-provoking for me listening to all this. Considering that incredibly specific condition for the prism function Taylor ratio, to be harmonic, that Pythagorean-like relation add 2 equals A12 plus add 12, it makes you wonder how many other fundamental geometric shapes or configurations might be out there, quietly harboring these hidden, non-trivial harmonic functions.
That's a great question.
Functions just waiting for mathematicians to meticulously uncover the precise conditions, the specific algebraic constraints like that sum of squares, and perhaps even the explicit formulas that govern their very existence. What new insights might these discoveries unlock, not just within the realm of pure mathematics itself, but perhaps in far-reaching fields like physics, where wave phenomena and potential fields described by Laplace's equation are so critical, or even engineering applications? What stands out to you as you reflect on this journey through the paper? Welcome, curious minds, to another deep dive into the profound elegance of mathematics. Today we're tackling a question that, at first glance, seems to defy intuition. Can a function exist that is non-zero almost everywhere, yet completely vanishes on a specific, non-trivial set? It sounds like a mathematical magic trick, doesn't it?
It really does. It has that paradoxical feel. But as you said, in the fascinating world of harmonic functions, this isn't just a possibility. It's actually a deep and, well, historically rich area of inquiry that has intrigued mathematicians for nearly a century now.
So we're stepping into the realm of solutions to Laplace's equation. These are functions where the Laplacian operator gives you precisely zero.
Exactly. And for those who, navigate these waters regularly, you'll recognize harmonic functions as the quintessential representations of steady-state distributions.
Like temperature in a room.
Precisely. Imagine the temperature in a room that has reached a perfect, unchanging equilibrium, or maybe the smooth electrostatic potential in a region devoid of any charges. What gives them this unique status is their inherent smoothness.
Okay.
They literally balance their values over space. This means they exhibit incredibly well-behaved, almost ideal characteristics. They average themselves out locally.
That balancing act is exactly what makes them so useful, right? In physics,
engineering.
Yeah.
They pop up everywhere.
Absolutely. They're smooth, they're elegant, and they describe so many fundamental phenomena.
But our focus today isn't just what harmonic functions are. We're digging into their intricate behavior when they intersect with zero. We're talking about the zero sets.
Or nodal sets. Yeah.
Nodal sets, right. And the central question guiding our exploration is really pointed. What specific configurations, points, lines, surfaces, what kinds of sets can a non-zero harmonic function completely vanish on?
And it's a surprisingly profound question. It's led to some truly unexpected and, I have to say, beautiful answers over the years.
And our mission in this deep dive is to meticulously unpack the brilliant insights presented in Ioann Vasilyev's paper on the zero sets of harmonic polynomials.
A fantastic paper.
It really is. And this isn't just, an academic exercise. Vasilyev's work is a tour de force. It offers rigorous mathematical arguments, intricate proofs, and some truly surprising constructions that directly provide a definitive answer to a long-standing, almost legendary challenge.
You're absolutely right. We're talking about problem 151 from the Scottish book.
Ah, yes. The Scottish book. For those who might not be familiar, this isn't a textbook, is it?
Not at all. It's famous, almost mythical. A collection of open problems in mathematics born out of the Scottish cafe in Poland back in the 1930s.
You can just picture it, can't you?
Yeah.
Mathematicians like Banach, Ulam, others gathered around posing challenges.
Exactly. And recording them in this notebook, often with these whimsical prizes attached.
Like a bottle of wine
Or in this specific case, a fondue in Geneva. That was the prize for solving problem 151.
a fondue in Geneva. I love it. And Wyeth's problem in particular remained a stubborn enigma for decades.
It really did. A true testament to its, deceptively simple phrasing, but profound complexity. Vasilyev's paper doesn't just chip away at it.
No, it delivers.
It delivers a comprehensive answer.
Yeah.
And we are going to explore the precise mathematical machinery he employed to achieve this breakthrough.
Okay, let's begin. Let's define the landscape. When we talk about harmonic functions, formally, what are we dealing with?
Formally, we're considering a real valued function. Let's call it f. It's defined within some open domain, let's say A, in d-dimensional Euclidean space, Rd.
Okay.
And this function f is designated as harmonic if its Laplacian, denoted f, is identically zero everywhere within that domain.
And the Laplacian, just to remind everyone, that's the sum of the second partial derivatives with respect to each coordinate.
That's right. F sum k1 to d f x a t u2. And this sum has to be zero at every single point in k. It's a condition that forces this profound local averaging property onto the function.
And flowing directly from that definition, we get this crucial concept of a uniqueness set.
Yes, a uniqueness set. For a given space of harmonic functions, HA, a subset S within A is called a uniqueness set if it satisfies a really powerful condition.
Which is?
If a harmonic function f vanishes identically on S, meaning fx equals 0 for all x and s, then f is compelled by this condition to be identically 0 throughout the entire domain.
So if it's 0 there, on that set S, it has to be 0 everywhere in A.
Exactly. If a harmonic function is 0 on a uniqueness set, it has no mathematical choice but to be the 0 function globally.
What's immediately striking, though, maybe a bit counterintuitive, is how powerful the maximum principle is for harmonic functions here.
Oh, absolutely. The maximum and minimum principle is key.
Consider this. If a harmonic function vanishes on something as seemingly modest as an open set, like even a tiny little ball within an A, or even just along a closed rectifiable curve,
Right.
the maximum principle immediately says that function must be identically 0 throughout the whole domain.
It does, because harmonic functions can't attain a strict local maximum or minimum inside their domain unless they're constant. So if they're 0 over a whole region, or even along a closed loop where they'd have to have a max or mads if they weren't 0, they're essentially pinned to 0.
The maximum principle just propagates that 0 everywhere.
Precisely. And this phenomenon immediately highlights why the sets we're really interested in today are non-trivial.
We're not looking for those easy cases.
Yeah. The real mathematical challenge and the focus of Vasilyev's paper is identifying and describing those specific non-trivial sets where a non-zero harmonic function can exist while vanishing on that set.
Okay.
The paper explicitly points out that a general, comprehensive description of these uniqueness sets for HRD, the space of harmonic functions across all of R, remains largely out of reach.
Even for seemingly simpler things, like finite unions of affine subspaces.
Even then, the complexity just scales dramatically with the dimension d. It's a tough problem.
Now let's bring that complexity into sharp relief.
Let's contrast it with the planar case, D2.
Ah, yes. In 2 dimensions, the corresponding question about non-zero harmonic functions vanishing on specific sets is, as the paper says, quite directly, rather easy.
Rather easy. Why is that? What makes 2D so different?
It's an elegant demonstration of the power of complex analysis in 2 dimensions.
Okay.
Imagine we have a finite collection of distinct points in the complex plane, C. Let's call this at E labels about E, where J goes from 1 to N.
Right, a finite set of points.
We can then construct a polynomial, let's call it PE, just by taking the product of the terms ZPJ for each J. So PE, product J1 to N CPJ.
Got it. Standard polynomial construction.
By its very construction, this polynomial P is holomorphic, meaning it's complex differentiable everywhere. It's generally non-zero except...
Except at the points PJ.
Exactly. It vanishes exactly at the specified points in the set E and nowhere else.
And here's the connection to harmonic functions.
The beautiful connection. We know that the real part of any holomorphic function is automatically a harmonic function.
That's a fundamental result from complex analysis.
It is. So if we just take re-PE, the real part of our polynomial, we get a function that is unequivocally harmonic throughout the complex plane, R2. It's generally non-zero outside of E, and crucially, it vanishes precisely on that finite set of points E.
So for any finite set of points in 2D, we can always find a non-zero harmonic function that vanishes exactly there.
Yes. We have an explicit construction, and this provides a vivid, almost jarring contrast to the immense difficulty we face in higher dimensions, where such straightforward direct constructions simply don't exist.
It really highlights a fundamental difference in behavior as we go from D2 to D3.
It does. And this distinction brings us right back to that historical challenge, Roland Wave's problem 151 from the Scottish book.
Posed November 6, 1936. With the Fondue Prize.
With the Fondue Prize, yes. The original phrasing, I believe it was in French, is added to its allure and enigmatic status for decades.
Can you remind us of the exact question?
The question was, does there exist a harmonic function defined in a region which contains a cube in its interior, which vanishes on all the edges of the cube? One does not consider f equals a 0.
So find a non-zero harmonic function that's zero on all the edges of a cube inside its domain. Seems simple enough to state.
Deceptively simple. It encapsulates a profound topological and analytical puzzle that remained unsolved for, well, nearly 80 years. It teased generations of analysts.
And that is precisely where Vasilyev's paper delivers its monumental breakthrough.
Yes. He provides a resounding positive solution to problem 151, specifically demonstrating its truth for dimensions d greater than or equal to 3. Theorem 1 in his paper states it clearly.
Let's hear it.
For any natural number d3, there exists a non-zero harmonic function on the whole space R, which vanishes on the d2 skeleton of the unit cube QD. This is the direct answer.
Okay, the D2 skeleton, let's unpack that technical term. What does it mean physically, say, for a cube?
Right. So the K skeleton, SKD, of a d-dimensional unit cube, which we can think of as QD equals 12 12, is formally the union of all its K-dimensional faces.
Faces like squares, edges, corners.
Exactly. More precisely, it's the set of points on the boundary of the cube that have at least dk of their coordinates fixed at either negative 12 or plus 12.
Okay, so for the D2 skeleton, K equals DD2. That means points must have at least D2 coordinates fixed.
Which is 2. So points on the D2 skeleton must have at least 2 coordinates equal to plus minus 12.
Let's make that concrete. For D3, our normal 3D cube, the D2 skeleton is the 3-2 skeleton, which is the 1 skeleton.
And the 1 skeleton of a 3D cube is...
just the union of all its 1D faces. The edges, all 12 of them.
Precisely. So for D3, Vasilyev's theorem definitively states that a non-zero harmonic function exists that vanishes on all 12 edges of the unit cube. This directly and elegantly solves Wav's original problem.
That's fantastic, and it's absolutely critical to highlight the remark that follows Theorem 1 in the paper.
Yes, very important. It explicitly states that this theorem is just false for the D2 case.
So it doesn't work for a square in 2D. You can't have a non-zero harmonic function vanishing on all 4 edges of a square.
Correct. And this categorical falsity in 2D is, as we discussed, a direct consequence of the maximum principle. You can't pin the function to 0 on the entire boundary, the edges, without forcing it to be 0 everywhere inside.
This distinction is paramount. It really hammers home how the analytical behavior shifts dramatically as we go from 2D to 3D and higher.
It makes these higher dimensional solutions so much more significant and, frankly, non-trivial to find.
So how did Vasilyev find such a function? He constructs a specific candidate, FDX.
He does. For a point x by 1a is xd and or a d, The function is defined by the formula, FD I1 I to D. Product 1 is ij by O2 I is J2.
Okay, the product of the differences of the squares of the coordinates taken over all pairs.
Exactly. And when you look at the structure, product I by I2 I is J2, it immediately brings to mind the classical Vandermonde polynomials.
Right. Those are usually product I.
Yes. And this isn't just a superficial resemblance. This connection, substituting E with by I2, is the profound algebraic backbone of the proof. It hints at deeper algebraic properties that are absolutely fundamental to showing FD is harmonic.
Before we get to the harmonic part, let's rigorously check that this FD actually does vanish on the D2 skeleton, as Theorem 1 requires.
Good idea. Let's verify that geometric requirement. Recall our definition. For a point X to be on the D2 skeleton, at least two of its coordinates must be fixed at either plus 12 or negative 12.
Okay.
Let's pick any two such coordinates, say xk and s. If both xk and SL are plus minus 12, then their squares, xk2 and vicel2, are both equal to 14.
Right. 12.2 and nh12.2 are both 14.
So the specific term sk2 by L2 within the product definition of FDX becomes 14, 14 equals 0.
Ah, and since FDX is defined as a product.
The moment any single term in that product is 0, the entire product FDX becomes 0.
Elegant. So it definitely vanishes on the D2 skeleton. The geometric part checks out.
It does. It fulfills that requirement with precision.
Now, the paper mentions FD isn't the only solution.
That's right. It's noteworthy. Vasilyev points out another related function, gx I will she way 1 point xd. Product 1 equals IJD by I2 par J2. This gx also works.
So multiplying by all the coordinates first,
Yeah.
that also satisfies the conditions. Interesting.
It is. And this observation immediately opens up a fascinating and complex open question also posed by Vasilyev. Can we comprehensively describe all harmonic functions that vanish on the edges, or the D2 skeleton of the unit cube?
Suggesting the solution space is much richer.
Exactly. It's likely far more diverse than just these two examples.
And there was another fascinating side note in the paper about a related Laplace eigenfunction.
Ah, yes, hx ey1.exd, product at xj. This function satisfies ix dhx.
So its Laplacian isn't 0, it's d times itself. It's an eigenfunction of the Laplacian with eigenvalue d.
Correct. So it's not harmonic and therefore not a direct solution to Wyver's problem.
But it shows a similar product structure.
It does. It demonstrates another intriguing connection between these characteristic product forms like Vandermonde and operators like the Laplacian. It hints at a deeper mathematical family at play, even if the specific properties differ.
Okay, so we've got the function FDX. We know it vanishes where it should. But the absolutely pivotal piece is proving it's actually harmonic. FDD equals 0.
This brings us directly to what the paper rightly calls its main technical auxiliary result, lemma 1. This is where the core mathematical heavy lifting happens.
Lemma 1. What does it state formally?
Lemma 1 states, let FD be as defined above and let dA2 be a natural number. We have ADX 0 for all x in RES, where sum HAX AK2 denotes the Laplacian operator.
And the paper emphasizes this is the key.
Unequivocally, it says the entire proof of Theorem 1 boils down to rigorously establishing this single lemma. Once FD is proven harmonic, the rest follows from the construction we already checked. This lemma is the beating heart of the solution.
And Vasilyev offers two different proofs for this lemma.
He does, which is quite nice. One is a more direct brute force computational approach.
Which sounds potentially messy.
It can be, managing all the derivatives and cancellations. It's doable, but prone to errors and maybe less insightful.
But the second proof?
The second proof is a masterclass in elegance. It leverages a powerful pre-existing property of the classical Vandermonde polynomial and its interaction with a specific differential operator.
That sounds much more interesting. Let's focus on that one.
Agreed. It truly showcases the power and interconnectedness of advanced mathematical tools.
Okay, walk us through it. Step 1.
Step 1 is to formally define the classical Vandermonde polynomial, which will denote Vy. For a vector y, y1 near d, in R, it's given by Vy. Product 1, ij, Vij.
The standard definition is the determinant of a Vandermonde matrix, right?
Exactly. It's a fundamental object, its properties are well studied, and Vasilyev cleverly exploits these established properties.
What's the crucial property here?
The truly crucial piece comes from a significant result by Koenig and O'Connell, Lemma 3.1 in their paper. It reveals a powerful identity.
Okay.
It states that for any arbitrary triple of constants, ABC and R3, a specific differential operator, let's call it LABC, has the remarkable property of annihilating V.
Annihilating meaning it sends it to 0.
Precisely, LABC VY import 0 for all Y and RD.
And what does this operator LABC look like?
It's defined as LABC sum I1 to D, YO2 plus AE plus B plus sum I1 to DC.
Wow. Okay, that looks involved. A sum involving second derivatives multiplied by quadratics in E plus first derivatives, and this always gives 0 when applied to V.
On any ABC, it's a profound identity, a pre-existing piece of deep mathematical knowledge that becomes the linchpin here.
So how does Vasilyev use this? He must pick specific values for ABC.
He does. He makes a precise and strategically brilliant choice. A, B, B0, and C12.
Okay, A0, B0, Z12. How did that simplify the operator L?
Let's see. With SEM B0, the quadratic term, YO2 plus AAI plus B, just becomes IO2.
Similar.
And with C2 of, the coefficient in front of the first derivative term FE becomes 12. So the annihilating identity L000Vy becomes so I1 to D YI2 plus so I1 to D12 VEY0.
Okay, that looks a bit cleaner.
And just to make it even more convenient for the next steps, let's multiply the whole equation by 2 to clear that fraction.
Good idea.
That gives us really 2 sum I1 to D EUI2 plus sum I1 to D V0. Let's call the specific operator M.
So MVY, EEO for all y. This specific combination of second derivatives weighted by 2i2 and first derivatives, when applied to the Vandermonde polynomial, is identically 0.
Exactly. That's the first critical equation we need. MVY equals 0 holds universally for Vy.
Okay, that's part 1. Establish this annihilating operator M. What's part 2?
Part 2 is to meticulously calculate the Laplacian of our target function, f dx, using the chain rule.
Right, f dx was product A by I2, ij2, and we noted this is V by 12 by 22 xt2.
Correct. Let's use that substitution, used I2 again. So f dx is Vy1 by 1 Ea dxt.
And we want a dx sum I1 to D minus by I2 f dx. So we need to compute each st1 term.
Let's do it carefully. First, the first partial derivative with respect to c is VO ETO UYYD DT.
And since y is CC2, then DETU is 2IR.
Right. So UC by 12 ID2. Let's keep that handy.
Okay, first derivative done. Now for the second derivative, 2c side I2. We differentiate that expression again with respect to IC.
2c by 12 I AFD2.
Looks like a product rule is needed here. The first part depends on IC through y side 2, and the second part is 2i.
Exactly. Let's apply the product rule. Derivative of first, second, plus first, derivative of second.
Okay, derivative of the first part. ECV by 12, EC2. That needs the chain rule again.
It does. It's 2VI2 by 12I2. EC2 is IIT.
Which is 2VI2 by 12 AFD2 DCI.
Good. So the first term of the product rule is 2VI2 by 12 by 12, or 2Li.
Which simplifies to 4 by I2. So VI2 by 12 XD2.
Okay. Now for the second term of the product rule. First part. Derivative of the second part.
The first part is EGUA by 12 xt2. The derivative of the second part, TPOEA with respect to E, is just 2.
Correct. So the second term is EGURI by 12 xd2.
Putting them together, the full second partial derivative is EKVOI2 so by I2 by 12 xd2 plus 2 UVO2 by 12 xd2.
Perfect. That's the expression for a single I.
Now we sum these up over all I from 1 to D to get the Laplacian ICD test.
Save A2, 4 by I2 by 12 xdd2 plus 2 VA by 12 xd2.
And I see a common factor of 2 in there. Let's factor it out.
Good idea. A dx, 2 sum I1, 2 VA2 by 12 xd2 plus U by 12 xd2.
Okay, wait a second. Look closely at the expression inside that summation. 2bi and 2 plus Yuri evaluated at xg2. Does that look familiar? It looks exactly like the terms in the operator M we defined earlier.
Precisely. Recall M v through sum I1 2 euro plus VA2.
So the expression inside the sum for f dx is just the ith term of M applied to V, but with U replaced by 2.
Exactly right. This is the elegant culmination.
And we established that MVY equals 0 for all possible values of y in Ard.
Yes. Universally true.
So it must be 0 even when we plug in U, the I2 for each I.
Correct. Therefore, the entire summation term, sum A1 to DI2 plus AU, must evaluate exactly 0.
Which means the Laplacian is E dx equals 2.
Which is 0. Wow. QED. That completes the proof of lemma 1 f dx is indeed harmonic.
It is.
That is genuinely beautiful. It transforms what looked like a potentially horrific calculation into, well, into just recognizing a known identity in disguise.
It really highlights the power of identifying underlying algebraic structures and leveraging existing deep mathematical tools. The property of the Vandermonde polynomial under that specific operator does all the heavy lifting.
A testament to mathematical artistry, truly. connecting polynomial theory and PDEs so elegantly.
It's a prime example of that kind of mathematical synergy. Okay, so Vasilyev definitively answered Wave's problem with FDX. But the paper doesn't stop there, does it? It moves on to constructing families of functions.
That's right. It shifts focus to another significant goal, constructing new families of harmonic polynomials that vanish at the same set in the unit ball.
So moving beyond just one function to understanding how groups of harmonic functions can share common, intricate zero sets, like building a framework.
Precisely. And the foundational concept introduced here, central to this construction, is that of harmonic morphisms.
Harmonic morphisms, what are they intuitively?
Intuitively, a harmonic morphism is a special kind of mapping, a transformation between Euclidean spaces that, in a very precise way, preserves harmonicity.
Preserves harmonicity, meaning if you start with a harmonic function
and you compose it with the harmonic morphism, the resulting function is also guaranteed to be harmonic.
Okay, so they map harmonic functions to harmonic functions via composition.
Exactly. It's an exceptionally powerful algebraic and geometric tool for systematically generating new harmonic functions from existing ones. A fertile ground for discovery.
And the paper lays this out in Proposition 1.
Yeah.
What's the setup there?
Proposition 1 starts with a compelling premise. Imagine you have an infinite, linearly independent family of harmonic functions, Sj3 for J1, 2, all defined in Rn where n is 3 or more.
Okay, a family Fj in Hrn and 3.
And a crucial condition. All these functions must share the exact same zero set in a localized region near the origin.
Meaning there's some small ball around the origin, B0, the AE, where the intersection of the zero set of any phi with that ball is identical to the intersection for any Fj, ZFJ, B0k. Yes, that establishes the starting point. A family with a common vanishing behavior locally.
Then what? We introduce the harmonic morphism.
Then we introduce spheorama, Rnn, which can be any non-constant harmonic morphism. Proposition 1 then details 3 critical consequences.
Consequence number 1. 1. The composition FJO is harmonic in arm for all j. Note the direction change. Phi maps from arm to Rn, where Fj lives. So the composition FJO is a function on Rm. This is essentially the definition of phi being a harmonic morphism. It pulls back harmonic functions to harmonic functions.
Okay, composition preserves harmonicity. That makes sense from the definition. Consequence 2.
2. The newly formed family FJO remains linearly independent. This is non-trivial and vital.
Why is that guaranteed? Couldn't the mapping somehow collapse them onto each other?
Good question. The proof relies on a fact cited from another source. Non-constant harmonic morphisms between Euclidean spaces are always open mappings, and specifically they are surjective if M afterly n, because phi maps Rm onto Rn, or more generally doesn't collapse dimensions too much. It doesn't cause the composed functions to lose their linear independence if the original Fj family was already linearly independent.
Okay, so linear independence is preserved. That means we're genuinely generating distinct functions. And the third consequence?
3. The composed functions, FJO phi, also share the same zero set near the image of the origin under phi. If Fj vanishes on a certain set Z near the origin in Rn, then FJO will vanish on the preimage set 1Z near 10 in Ro. Since all Fj share the same Z near the origin, all FJO will share the same preimage set near 10.
So the shared zero set property is also carried through the composition. This provides a systematic method for building families with controlled vanishing behavior.
Exactly. It's a powerful engine for construction.
Building on this, the paper then gives concrete examples in the proof of theorem 2. Let's look at the even dimensions first, R2k for KR2.
Right. For this case, Vasilyev defines a specific harmonic morphism, do R2n FER2. Note the paper uses n in the proof corresponding to k in the theorem statement, so it's R2n mapping to R2, which we can identify with the complex plane C.
Okay, R2n to R2, what are the components 1 and 2?
They have this elegant alternating structure.
By 12 by 22 plus by 32 by 42 plus by 2 n to 1 and 2 n x 2 by 1 by 2 plus 2 by 3 by 42 plus 12 plus 2 by 2 n by 2 n plus 2 by 2 n 1 by 2.
Ah, those look familiar. If we think of Zj by 2j1 plus I by 2, then Zj2 plus I 2 by 2j1 by 2. So 1 plus I2 is just some j1 to n to j2.
Exactly. It's a well-known harmonic morphism, often related to complex quadratic forms. The paper cites reference 21, theorem 5.11, to formally confirm is indeed a harmonic morphism.
And what's special about 1x itself?
1x is described as an irreducible, non-degenerate, quadratic, homogeneous, harmonic polynomial. Let's break that down.
Okay. Irreducible means?
Cannot be factored into simpler non-constant polynomials over the real numbers. Non-degenerate means it doesn't collapse or vanish identically. Quadratic homogeneous means degree 2, all terms have degree 2, and it genuinely depends on all 210 variables.
So it's a fundamental building block polynomial, and the crucial consequence...
Then divides infinitely many linearly independent harmonic polynomials.
How does that work? How can one polynomial 1 be a factor of infinitely many different harmonic polynomials?
The paper gives a stunning example using the complex structure we just noted. Consider 1x plus I2x. Since this is holomorphic in the complex variables, zj, any analytic function of it, like 1x plus I2xk, will also be holomorphic, and thus its real and imaginary parts will be harmonic in the x variables.
Okay.
Specifically, the paper suggests looking at n1x plus I2x2k for natural numbers k. This k is just an index, different from the dimension n or k. Each of these functions for different k is a distinct, non-trivial harmonic polynomial in x.
And since 1x implies I'm 1x plus I2x2k might be 0 or related to powers of 2, they likely share the 0 set of 1.
Precisely. Or more accurately, if 1x equals 0 and 2x equals 0, then the whole complex expression is 0, so the imaginary part is 0. The 0 set of the family is related to the common zeros of 1 and 2. This construction using powers beautifully demonstrates how a single harmonic polynomial 1, or the pair 1, 2, can generate an entire infinite linearly independent family of harmonic polynomials sharing a common zero structure.
And this extends previous results.
Significantly, it extends work by Loganov and Malenikova, particularly in dimension 4, n2. Their earlier work used different techniques, focusing on axially symmetric functions. Vasilyev's use of harmonic morphisms provides a more general and extensible framework.
Okay, that covers the even dimensions. What about odd dimensions? R2k plus 1 for k equals 2? The paper uses m for the odd dimension, so m equals 5.
For this case, the approach cleverly draws from example 5.2.7 in reference 4, showing the interconnectedness of these ideas.
What's the construction here?
Here, they define a harmonic morphism from arm to C, the complex plane R2. Let x equals by 1, x 2x. Define a complex variable zx, x mans 1 plus ixm using the last two coordinates.
Okay.
The harmonic morphism, the m mans x, x 2x, is then defined as a sum involving the first m2 coordinates with coefficients that depend on z. Sum j1 to m del 2 m maps 2 xj, xj, x2, xj. Now, here xjz are complex valued functions of the complex variable z.
So it maps Rm to C? What's the condition for this to be a harmonic morphism?
The absolutely critical condition is that the sum of the squares of these complex coefficient functions, order jz, must be identically 0. Sum j1 to m2 orders j2.
The sum of their squares must vanish. Why is that needed?
That identity is precisely what ensures harmonicity is preserved under composition. It relates to the geometry of null cones in complex spaces, ensuring the mapping behaves correctly with respect to the Laplacian.
How do you find functions SGZ that satisfy this? Seems restrictive.
The paper points to a known ansatz, a specific form of solution from example 6.8.6 in reference 4. This provides a way to construct such a GJ.
What's the answer?
Let G or G, U or N2, EM2 be arbitrary polynomials or analytic functions of Z. Let G2 e.g. G12 plus GM toes 2. Then you can define the vector Anteo chase XUZ using a structure like this is simplified. The actual formula uses 3 components of M2, 3, etc.
1G2, I1 plus G2, negative 2G1, negative 2GM, negative 3, assuming enough components. The key is that standard constructions exist where sum negative 2 equals 0 holds identically. For example, using the structure 1G2, I1 plus G2 managed 2G for 3 components works. 1G2 plus I1 plus G2 plus managed G2 plus G4, 1 plus 2G2 plus G4 plus 4G2 equals 0.
So there are known ways to construct these Ashtray functions using arbitrary polynomials GJ such that the sum of squares condition holds.
Exactly. And once you have this harmonic morphism, 1, 2, from arm to C, you can essentially use it in place of the 1, 2 pair from the even dimensional case.
How? By composing with functions on C.
Yes, you can take powers 1 plus I for 2k and their real imaginary parts, similar to before. This systematically generates the desired families of harmonic polynomials sharing common zero sets, but now specifically in odd dimensions M5.
Why the restriction M? What about M3?
The paper remarks that while the general construction might technically apply for M3, this particular method doesn't yield the non-trivial examples of families they are aiming for in this section. The structure isn't rich enough in R3 for this specific ansatz.
In M4.
M4 is an even dimension, so it's already covered by the first case. 2k4 means k2. So for generating new families using this odd-dimensional method, the focus is justifiably on m equals 5.
The paper mentions other harmonic morphisms exist too.
Oh, yes. It emphasizes that this is just one way to construct them. It mentions many other non-trivial harmonic morphisms, pointing specifically to those based on Hopf polynomials and directing the reader to the comprehensive book 4 for much more detail.
So this is just scratching the surface of harmonic morphism theory.
It is, but it's a powerful application of that theory to the problem of constructing shared zero sets for harmonic polynomials.
Okay, we've covered the solution to Wave's problem and the construction of families using morphisms. But the paper also revisits some open questions, pushing the boundaries.
Absolutely, a hallmark of great research. It brings back that intriguing question posed implicitly after Theorem 1. Given an arbitrary finite union U of affine lines in R, under what precise conditions on the geometric configuration of U does a non-zero harmonic function f exist such that f vanishes identically on all of U?
That sounds much harder than the cube edges, which is a very specific set of lines.
It is, and it's deeply tied to a fundamental property of harmonic functions. They are real analytic.
Meaning infinitely differentiable, representable by power series locally.
Exactly, and this has a huge implication. If a real analytic function vanishes on even a small segment of an analytic subvariety, like a line segment,
It has to vanish on the entire subvariety, the whole infinite line in this case.
precisely, this analytical propagation is crucial. If a harmonic function is 0 on a cube edge, it must be 0 on the entire infinite line containing that edge. So the question about vanishing on lines is really about vanishing on infinite lines.
The paper mentions previous work on this.
Yes, it contextualizes by referencing Flatto, Newman, and Shapiro's work from 9. They looked into this, especially in the plane, D2, considering parallel lines and linear subspaces. So the general problem for lines has been around.
Vasilyev's paper dives into a specific planar case study in the appendix, the half strip.
It does. It explains how, in the plane, the powerful Schwartz reflection principle simplifies things.
Schwartz reflection, that lets you extend harmonic functions across straight boundaries under certain conditions, right?
Yes, by reflecting the function symmetrically. Using this, the paper argues that the only really tricky remaining case for 3 lines in the plane is when they form an orthogonal half strip.
Like 2 parallel lines cut perpendicularly by a third.
Exactly. If the third line wasn't orthogonal, reflections would quickly force the function to be 0 everywhere if it vanished on all 3.
So the challenge is this specific half strip H defined as
H by 1 by 1 by belt or 2, diagonal by 2, and alta by 1 by 1 by 1. So it's in the upper half plane by 2, 0, between by 1 by anoyo and by 1 by 1.
And the goal is to find a non-zero harmonic function 1, 0 that vanishes on the boundary of H.
And the paper presents an explicit formula for such an S0. Be warned, it's quite something.
Okay, I'm braced.
S0 by 1 by 2 cos sin by 1 plus sin 2 by 1 plus sin by 1 plus sin j by 12 sin by 1 cos by 1 plus sin 2 by 1 plus sin 2 by 2 12 sin to 1 1 plus 2 cos 2 by 1 sin 2 by 2 plus sin 2 by 1 plus sin 2 by 12 2 plus 2 by 12. Okay, that's intricate. Lots of trig and hyperbolic functions nested together.
It is complex. The paper tersely notes that verifying its harmonic and vanishes on the boundary is a routine computation.
Routine perhaps for a computer algebra system or someone very patient.
Quite possibly. But the real insight isn't just the formula, but how one might find it.
How?
The paper hints at using conformal mappings from complex analysis.
Ah, mapping domains again.
Yes, you can map the upper half plane conformally onto both the full infinite strip between by 1 or 1, 2, 2, and onto the half strip H. Then you combine this with known harmonic functions that vanish on the boundary of the full strip, like e by 1, sin by 2, or sin by 1, sin by. So you transform a known solution on a simpler domain, the full strip, back to the half strip using these mappings.
That's the idea. It shows the power of combining harmonic analysis with complex variable techniques. A change of coordinates via conformal mapping can unlock the solution.
Okay, moving beyond 2D again. Proposition 2 generalizes to 3D, talking about zero sets as boundaries of prisms.
Yes. The setup is, take W as the École Monéchese plane in R3, Let P be a bounded triangle within that plane W. And CP is the unbounded prism formed by extending P infinitely along the Gaiwan axis in both directions.
So the boundary CP consists of 3 infinite flat strips corresponding to the sides of the triangle P.
Exactly. And proposition 2 has 2 parts depending on the shape of the triangle P.
There's one.
Part 1 says, if P is not one of 4 specific special triangles,
I'm sorry.
equilateral, 60,000, 60, 60, isosceles, 30,000,000, 30,120, right, 30, 60, 90, or isosceles, right, 45 million, 45, 90.
Okay, if P is not one of those 4.
Then any harmonic function in R3 that vanishes on the boundary of the prism CP must be identically 0. The only solution is the trivial one.
So for most triangles, you can't have a non-zero harmonic function vanishing on the prism boundary. Why is that?
The proof relies on work cited in 5. It shows that for these non-special triangles, if you repeatedly reflect the triangle across its sides within the plane W, the vertices, or edges, of the reflected triangles become dense in the plane R2.
The reflections fill up the plane densely.
Right. And if the set where a harmonic function vanishes is effectively dense in a plane projected from the prism boundary, the maximum principle, in a more sophisticated form, forces the function to be 0 everywhere. The geometry prevents non-trivial solutions.
Okay, so what about part 2, if P is one of those 4 special triangles?
Then, proposition 2 states a non-zero harmonic function does exist that vanishes on the boundary of CP.
And why do these triangles work?
Because these specific triangles have a remarkable geometric property. When you reflect them across their sides, they perfectly tile the plane W without overlaps or gaps. Think of equilateral triangles, or squares made of 2 45, 45, 90 triangles.
They create a regular tiling, like bathroom tiles.
Exactly. Reference 10 showed a non-zero harmonic function exists inside the prism vanishing on the boundary. The Schwartz reflection principle then allows you to extend this function smoothly across the boundaries to the entire R3 precisely because the reflections tile perfectly. There are no inconsistencies or singularities introduced by the reflection process.
Wow. So the ability to tile the plane via reflection is the key geometric property that allows for non-trivial harmonic functions vanishing on the prism boundary. That's a beautiful connection between geometry and analysis.
It truly is. And as a concrete example, the paper again references Loganov and Melenikova. For the unit square, which can be made from 2 45, 45, 90 triangles, one of our special cases.
You gave an explicit formula.
Yes, for the corresponding prism in d dimensions, the function is 8x sin a1 by 1 dot sin ad1 x d1.
Okay. And this is harmonic
If the constants a1, x satisfy add 2 equals a12 plus a plus ad1, too.
Ah, like a Pythagorean theorem for the coefficients.
Sort of, yes. And it clearly vanishes on the prism boundary defined by, say, xj0 or xj goes for jd or xd0 because the sine or sin terms become 0.
Provides a nice explicit illustration of proposition 2, part 2.
Exactly. Bridges the existence theorem with a concrete formula for a special case.
And as is fitting, the paper concludes by looking ahead, highlighting remaining mysteries.
It does. It prompts for finding explicit formulas for prisms based on the other special polygons, like the equilateral triangle case, beyond the square. That would be valuable.
And a broader challenge.
An even more ambitious goal, to achieve a general classification of all non-zero harmonic functions that vanish on the boundary of a half strip or a half prism. Not just finding examples, but understanding the complete structure and behavior of such solutions.
So moving from existence to a full characterization.
Precisely. These open questions really underscored that even in a field as seemingly classical as harmonic analysis, fundamental problems continue to drive new discoveries, constantly pushing the edges of our understanding.
Okay, let's try and bring the threads of this deep dive together. We started with this almost paradoxical question. Can a non-zero harmonic function vanish on a significant set? Which led us straight into Roland Wave's century-old challenge, Problem 151 from the Scottish book, a puzzle that lingered for decades.
And we saw in detail how Ioann Vasilyev provided that resounding yes for dimensions 3 and up, constructing his FDX function.
The proof was a highlight, leveraging the Vandermonde polynomial and that annihilating operator. A beautiful example of algebraic structure solving an analytic problem.
Absolutely, showing deep connections between seemingly disparate fields.
Then we saw how Vasilyev went further, using harmonic morphisms to forge entire families of harmonic polynomials that share common zero sets.
A powerful technique for systematic construction moving beyond single examples.
And finally, we explored the edges of current knowledge, the half strip, the prisms based on special triangles. Discovering the precise geometric properties, like tiling the plane by reflection, dictate whether non-trivial solutions can exist.
That interplay between the geometry of the boundary and the analysis of the function was striking.
So,
For you, our listener, diving deep into this with us, what are the key takeaways?
Well, first I'd say the maximum principle is powerful, yes, but it's not the whole story in higher dimensions. Non-trivial zero sets can exist.
All right. Dimension matters.
Second, abstract tools are critical. Properties of polynomials, geometric transformations like harmonic morphisms, reflections, these are indispensable for understanding harmonic functions.
It's not just about grinding out derivatives.
Not at all. And third, even in classical fields like harmonic analysis, fundamental questions can remain open for decades, driving new insights and revealing deeper structures.
It's a field where analysis, geometry, and algebra constantly interact, yielding these profound results.
Indeed, revealing the inherent order and beauty within these mathematical structures.
So here's a final thought to leave you with. Knowing what you now know about these vanishing functions, about their intricate existence and behavior, if you were tasked with designing, say, a multidimensional invisible cloak using harmonic fields, what fundamental mathematical property or constraint would be your biggest challenge?
Ooh, interesting question. Maybe the rigidity from real analyticity, or ensuring the vanishing holds precisely where needed without collapsing elsewhere.
And conversely, which tool or insight from today would be your most powerful ally? The specific construction, harmonic morphisms, the reflection principle.
Perhaps the ability to construct functions that vanish on specific complex geometries like Vasilyev did, or maybe the flexibility offered by harmonic morphisms.
Something to ponder. We definitely encourage you to explore the references in Vasilyev's paper if this has piqued your curiosity. There's a whole fascinating landscape out there.
There certainly is.
Until our next deep dive, keep exploring.